Hi, David, can you hear me?
Uh,
pause. Maybe if you'd like to test your mic or sharing, we could do that now. Thank
Okay.
you for
So
joining.
should I do the share thing?
We can try it out once before lecture now. Yes.
All right. So I click share. You are now showing
Mm.
share.
I see your computer
Let me
screen.
bring up my thing.
Yeah.
Your full screen. How does that work?
Yes, perfect. Now it's full screen. Oh, yes.
Okay. Should I just
That's
leave it
good.
this way?
Maybe we would like to make some, announcement and then introduce you, so you can
Okay. So I
unshare for
will.
now. Yes,
Okay. So let's see if
and
I
I'll
can
request you
remember
once
how
again
does this.
later. Maybe you can hit escape on your keyboard, then you can
I see. Okay.
also you should be able to get out of this.
There we go.
Yeah, and
And
then
I
you
can just
can stop
close all
sharing
this.
somewhere,
Okay.
and you should stop sharing. Oh yeah, okay,
Oh, yeah.
yeah, that's good. That's good. Thank you. Thank you so much. I'll see you in a bit. John, Professor John, is it possible to get, sorry, just that your light is a little bit lighter, like dim? Could you make sure that we can see you properly?
Oh, you want
Is
to
that
see me?
possible? I mean,
Oh,
just for the
oh,
audience, if
make my
yeah, if you
room
can
look
make your
brighter.
light brighter, yes, exactly.
Yeah,
It would
especially
be much
if
better.
light comes on his face, that will be great.
Yes. Okay, this is already good, I guess. Yeah.
So you see me now?
Yes, yes, we see you.
Okay.
Thank you. Yeah.
that okay?
The universe is marvelous.
Yes,
Just look
good.
at the sky. Huge planets, bright stars, vast galaxies, massive clusters. It just fills us with tremendous amazement. In the last century, our exploration of the cosmos has reached unprecedented depths. From the first echoes of the Big Bang to the accelerating expansion of space, from dark matter and dark energy to ripples in space-time itself. Yet, with every answer, deeper questions have arisen. How far are we in understanding our universe? What lies at its beginning? Are there limits to knowledge, observation, and even comprehension? Is the astonishing order of the cosmos merely accidental? Or does its beauty, fine-tuning, and mathematical elegance point toward a deeper intelligence and purpose, as some of the greatest scientific minds have reflected across generations? To explore these profound questions, Bhaktivedanta Institute invites you to an extraordinary voyage through our cosmos, where some of the world's most brilliant scientific minds will share their insights and discoveries, including Andre D. Linde from Stanford University, John H. Schwarz, theoretical physicist, Caltech, USA, Wendy L. Friedman from the University of Chicago, Ofer Lahav from University College London, Avi Loeb, Harvard University, USA, Pankaj S. Joshi International Center for Space and Cosmology, India, and many more leading thinkers from across the globe. This is a space for rigorous science, open inquiry, and meaningful dialogue, where curiosity meets humility. Welcome back to your own astonishing home, the universe.
Amazing. So I think we can start now. So good evening, Professor John, because you are in the US and it's evening for you. Good morning to everyone else who are joining us in India. And a very warm welcome to all our guests, speakers, faculty members, and all our participants for joining us today from across the country and the globe for these Golden Jubilee lectures on Voyage through the Cosmos, History, Models, Theories, Latest Images, and Foundational Issues in Understanding the Universe. My name is Dr. Dipankar Sharma, and it is my privilege to be your host for today's program. So today is day 6 of this lecture series, which began on the 16th of March, Monday, and which will continue until tomorrow in online mode. So this brings together distinguished scientists, scholars, and brilliant thinkers around the world. This lecture series is organized by Bhaktivedanta Institute, Kolkata, as part of its Golden Jubilee celebrations, commemorating 50 years of dedicated service to humanity. Well, the timings you're all aware of. From Monday to Friday, we had sessions from 5 to 8, and today and tomorrow, these sessions are from 10 a.m. to 1 p.m. Indian Standard Time. So before we start, I would like to give you a quick review of our today's schedule. So we'll start with this amazing lecture by the legendary Professor John Schwarz, who is with us today from Caltech, USA, and he's one of the leading founders of string theory. He will provide a captivating personal perspective on a very interesting topic, which is titled String Theory in the 20th Century. Then we'll have a second talk by Mr. David Dilworth, who is formerly of the US Naval Postgraduate School. He will guide us through a masterclass which is titled Bubbles and Voids versus Fancies, a deep dive into the cosmic structures that define our reality. And the final talk for the day would be delivered by Shri Varun Agarwal, Director of the Bhaktivedanta Institute and alumnus of IIT Kanpur. He'll speak on the intriguing topic, Cosmology and Consciousness, Search for a Complete Story of Our Universe. So before I proceed, I'd like to remind and let our participants know that please scan the QR code. You will also receive a link in the chat so that you can ask your questions using this link provided. which later after the lecture, then I will deliberate them to Professor Schwarz during the Q&A session. So please. Now, it's my great pleasure to introduce Professor John Schwarz, our distinguished speaker for today's session. I will read out his quick introduction. John Henry Schwarz is a titan of modern theoretical physics and the Harold Brown Professor of Theoretical Physics Emeritus at the California Institute of Technology. Recognized universally as one of the founding fathers of string theory, he demonstrated unparalleled intellectual courage by sustaining the field during the 1970s when it was largely abandoned by the scientific community. His visionary collaboration with Zoel Scherk fundamentally redefined the discipline by proposing that string theory was not merely a model of nuclear forces, but a unified quantum theory of gravity, predicting the existence of the graviton within a consistent mathematical framework. Schwarz's most transformative contribution, the first superstring revolution of 1984, changed the course of physics history. Working with Michael Green, he provided the anomaly cancellation mechanism, demonstrating that superstring theory is free from the mathematical inconsistencies that plagued previous attempts at unification. This breakthrough established string theory as the premier candidate for a theory of everything, bridging quantum mechanics and general relativity. A recipient of the MacArthur Fellowship, the Dirac Medal, and the Breakthrough Prize in Fundamental Physics, Schwarz's legacy is etched into the fundamental understanding of the dimensionality and structure of the universe. So with this, I would like to invite Professor John Schwarz to present his talk today. I'm very honored and happy to have you, sir.
Thank you. So I will try to share my screen. Can you hear me?
Yes, yes, we can.
Okay. So I'll bring up my file.
Mhm.
And make it go full screen if I can. Okay. Is that
Perfect.
working?
Yes,
All
all
right.
good. Thank you.
So I guess you've already told people that my title is String Theory in the 20th Century, a Personal Perspective. So let me tell you about all the crazy things I've been involved in. So I've been invited to give a personal account of the early history of string theory, which is the period from 1968 to 1985. The story I'll relate is quite unusual. A theory that was developed with the goal of describing the strong nuclear force turned out to be a unified theory of all fundamental forces, including gravity. The equations have many possible solutions, though we do not have unique predictions, but it is plausible that one of them can describe our universe. That remains, of course, to be demonstrated. My contributions have benefited greatly from excellent collaborators, primarily Andre Neveu, Joël Scherk, Larry Brink, and Michael Green. The string theory originated in an attempt to find a theory describing the strong nuclear force. So this work was in the early 1960s, and at that time, the only force for which there was a satisfactory quantum theory was the electromagnetic force. And that theory, called quantum electrodynamics, or QED for short, is a well-established quantum field theory of electrons and photons, which is today just as well regarded as it was back in the 1960s. Now, the goal of the high energy theory group in Berkeley, when I was a graduate student a long time ago in the 1960s, was to construct a theory of strongly interacting particles. And these particles are referred to as hadrons. The most familiar examples are the proton and the neutron. The correct theory of hadrons, named quantum thermodynamics, or QCD for short, was formulated in 1973, so later than the period I'm talking about now. And it is a quantum field theory of interacting quarks and gluons based on a Yang-Mills gauge group SU3. Now, for reasons I'll explain, it's fortunate that QCD wasn't discovered a few years earlier. Had it been discovered earlier, string theory might not have been developed for a very long time. Geoffrey Chu, who was my PhD advisor, proposed in the early 1960s that one could deduce the theory of hadrons from some general principles, including unitarity and analyticity of the S matrix. The S matrix is an infinite dimensional matrix that encodes all possible scattering processes. And unitarity ensures that all possible outcomes of an interaction have probabilities that are positive and add up to 1. Analyticity ensures that the dependence on the initial and final momenta is sufficiently smooth. Any singularities should have a physical interpretation. So to just give you a little sense of what the formulas looked like, let me just review some basic kinematics that I'm sure most of you already know. So we wish to determine a quantum mechanical amplitude, say for a relativistic reaction in which particles 1 and 2 collide and particles 3 and 4 emerge as a result. So representing the 4 momentum of the nth particle by p sub m sub mu. So mu runs over 0, 1, 2, 3. 0 represents energy, so p0 is energy, and 1, 2, 3 are the 3 components of the momentum. The conservation of energy and momentum in the process 1 plus 2 goes to 3 plus 4. It's just the equation, the obvious equation at the bottom. Now, setting the speed of light equal to 1, special relativity implies dot product of or the square of a momentum given by the dot product, which has this minus sign corresponding to the signature that you have in relativity, is equal to the mass squared. In the case of zero momentum, this just says the energy is the mass, which is, of course, famous, Einstein's famous E equal mc squared. We've set c equal to 1 after all. So one also defines invariant variables, S, which is P1 plus P2 squared, T, which is P1 minus P3 squared, and U, which is P1 minus P4 squared. And in simple algebra, it tells you that the sum of ST and U is the sum of the squares of the masses. So these 3 things are not independent. They have this relationship. So the goal was to determine a quantum mechanical scattering amplitude denoted A of S and T for a reaction in which particles 1 and 2 collide and give particles 3 and 4. So Chu and Frautschi in the early 60s proposed that in the case of hadrons, which is what we're talking about, particle exchanges provide the forces that are responsible for the particle's own existence. They found this reminiscent of a tale about a man who lifts himself up by his own bootstraps, which is, of course, absurd. But that analogy or example motivated this name for the conjecture. So this kind of a setup is quite different from conventional quantum field theory, because in conventional quantum field theory, one adds together the contributions of Feynman diagrams, which describe particle exchanges in all the different channels, S, T, and U. And this picture says that you can, if you just do it in one of them, you can deduce the others. So the big breakthrough really started with a formula that was written down in 1968 by Gabriele Veneziano. He discovered a formula that gives an explicit realization of the bootstrap principle and as well as other desirable properties. And a slightly simplified version of his formula is what I've written down here. So A is the amplitude we want. D is just a coupling constant, just a number. And V is Euler's beta function, which is given by some combination of gamma functions, also due to Euler, which, as you probably know, give a continuous interpolation for the notion of a factorial. The Regge trajectories, so these functions alpha are called Regge trajectories, and they're just linear functions. So alpha of x is the intercept alpha 0, and then it has a slope alpha prime s. So this extremely simple formula satisfies the bootstrap equations. And what that means is if you take this function and expand it in terms of the poles in the S channel, in the variable S, that's sum gives you back the entire function. But this formula has symmetry, so the same thing is true for the T channel. And to add, if you were to add those two contributions together, that would be double counting. So this is in contrast to conventional quantum field theory, where you would treat the poles in all the different channels separately. Soon thereafter, Virasoro proposed an alternative formula, which looks a little more complicated, but it's not much, just a different combination of these gamma functions. And amazingly, these two guessed formulas, just pulled out of the blue, turned out to be almost precisely the amplitudes for open string and closed string scattering that were soon found afterwards. In the modern interpretation, they correspond to gauge theory and gravity interactions, respectively. Now, the n-particle generalization of the Veneziano formula was found in 1969, just the next year, by several different groups simultaneously, more or less. And it's given by this little more complicated formula, but it's not too bad once you get into the stuff. Mu n is a measure which contains 3 delta functions, so that they're really only n-3 integrations, and restricts the variables such that the j plus first coordinate is larger than the j plus, because this has the appropriate step functions in it. So by a change of variables, this formula can be recast in a form in which the n-particle positions are at points on the boundary of a circular disk instead of an infinite line, which is the way it's written in the formula that I presented. So when you put them on this, when you make the change of variables to put them on a circle, then they have a specified cyclic ordering, which corresponds to these step functions I was discussing earlier. The particles in the previous formula only are required to belong to the adjoint representation of a gauge symmetry group, such as an orthogonal group or a symplectic group. And the complete tree approximation amplitude then takes the form of a sum of these n-particle amplitudes I've shown you with different permutations of the ordering of the particles and appropriate group theory coefficient, which are given by traces of products of matrices as the coefficients. Soon thereafter, Shapiro found a similar formula, which generalized Virasoro's formula, and it involves n-3 complex integrations. So the previous formula had dx's, this has d2z's. So this is twice as many integrals as the previous formula. And again, this measure involves some delta functions so that 3 of the z's can be fixed at specific positions. But now the remaining z's do not have an ordering. They can take arbitrary complex values. And so these particles described by this formula are singlets of the gauge symmetry groups. So they're invariant under the gauge symmetry. And this formula can be recast in an alternative way in which the n-particle positions are all at points on the surface of a 2-dimensional sphere. But you can get that again by a change of variables. So the next development, this was really all quite amazing. This next development was that Fubini and Veneziano showed that these formulas have an internal consistency. Specifically, if you look at the poles in the formulas and take the residues of these poles, they factorize in terms of a well-defined spectrum of single particle states. And these single particle states can be described using an infinite number of harmonic oscillator operators. These harmonic oscillator operators have two indices on them. One runs over the directions of space and time. So 1, 2, 3 are the spatial directions. U equals 0 refers to the time direction. And the index m goes over all the positive end numbers. So there are an infinite number of these oscillators. And so these oscillators generate some enormous Fock space, which is roughly the spectrum of the theory. Now, there's one set of such oscillators in the Veneziano case and two sets in the Shapiro-Virasoro case. So what I've described here refers to the Veneziano case, and in the Shapiro-Virasoro case would be a second set of oscillators that would have identical property to these. The fact that there is a consistent factorization with a well-defined spectrum of particles was the first indication that all these marvelous formulas are actually representing a theory and not just an intriguing collection of formulas. Because until this work of the Fubini and Veneziano, you had these beautiful integrals and everything, but they were just made up formulas. And now the factorization of the states with its oscillator description made it clear that these formulas actually came from an underlying theory. So the next question is, what is the theory? So in 1970, Van Boo, Nielsen, and Susskind independently interpreted the formulas as arising from a theory of a relativistic string. So it's an open string. So these strings are infinitely thin. So they're really one-dimensional objects. And there are two possibilities. One is that they have two ends, and that's the kind of string called an open string, and it's relevant to the Veneziano case. And the alternative is you have what we call a closed string, which just means it's topologically a circle, but it can wiggle around arbitrarily. And it's the kind of string whose quantization leads to the Shapiro-Virasoro amplitudes. So these strings, when you think of their time evolution, sweep out two-dimensional world sheets in space-time. So the strings are one-dimensional. Their evolution gives a two-dimensional surface. Whoops, sorry. In space-time. So the open string particles attach to the boundary of a world sheet, and closed string particles attach to the interior of a world sheet. So having found the spectrum and tree approximation amplitudes of the string theory, it became possible to study quantum corrections or loop amplitudes. So these are completely analogous to what one does in ordinary quantum field theory, where using Feynman integrals, it starts with tree amplitudes and then constructs quantum corrections given by diagrams that have loops. So do the same thing, except instead of the particles being points that give lines in space-time, we have objects which are strings, which sweep out two-dimensional surfaces in space-time. Anyway, these are given by integrals. When you go to these loop amplitudes, the two-dimensional surfaces, which stay in the closed string case, for example, where a sphere in the tree approximation will now be higher genus. So the one loop case would be a torus, and then you would have more holes as you go to higher genus. And beyond one loop, the math gets really nasty. But at one loop, it's still manageable. So after graduating from Berkeley, I spent 6 years in Princeton before I moved to Caltech. And I followed all the developments I've been telling you about with great interest. But my first significant contribution was in 1970 in a paper that I co-authored with 3 people, David Gross, André Neveu, and Joël Schuck. So the 4 of us wrote a paper that studied open string one loop amplitudes. So the world sheet that we considered is topologically a cylinder with 2 circular boundaries. And there were 2 cases of interest that we considered. In the first case, all 4 particles in a 2-to-2 reaction are attached to one of the boundaries. And in the second case, 2 of them are attached to one boundary and 2 of them are attached to the other boundary. In the first case, the integral diverges, and this divergence can be removed by a well-understood, non-controversial procedure previously introduced in a paper by Naval and Schwarz. So that case is okay. And it's the second case that turned out to be more profound. So in the second case, where you have 2 particles on each boundary, we were able to do the calculation, and we found that the amplitude contains branch points in the coordinate s equals p1 plus t2 squared. So, and that the existence of these branch points violate the unitarity principle, which is absolutely sacred for making sense of this stuff as a quantum theory. So unless one could somehow eliminate these branch points, this could not be a consistent quantum theory. So this is a real serious problem. And for a while, at least, it looked like this whole business was dead. But a few months later, physicist who was at CERN at the time, Claude Lovelace, rescued the theory by observing that these singularities would become poles, which would have a sensible physical interpretation rather than branch points. If we took this function alpha of s that I discussed earlier, it took the constant term alpha 0 to be 1, so that has to be 1. So that's necessary, but even more dramatically, they found that it will only get poles if the dimension of space-time was 26. This was absolutely extraordinary, because nobody working in this subject had ever considered any dimension other than 4 before this, and it seemed absolutely nuts. Why should the strong interactions want 26 dimensions? So Lovelace's discovery forced us to take extra dimensions of space, 22 of them in this case, seriously for the first time. But why should hadrons require extra dimensions? And why should the open spectrum, alpha 0 equal 1 implies that there's a massless spin 1 particle in the spectrum. Why should an open string spectrum have that property? So so even though we had what looked like a consistent theory, it certainly didn't look like the theory of hadrons that we wanted, both because of the space-time dimension and because there was a massless particle in the spectrum. So the new poles that Lovelace forced us to understand describe closed string intermediate states in the reaction 1 plus 2 goes to 3 plus 4. So when you have a cylindrical world sheet, there's 2 ways of thinking about it. It can be viewed either as a loop of open string. So you have a string with ends and you bring it around in a circle, and that makes a cylinder. Or you can take a circle and propagate it for a certain finite distance. So you're taking a closed string, moving it for a certain distance, and that also gives a cylinder. And so the 2 different ways of thinking of it means that the process can be viewed as a loop of open string or just the propagation of a closed string. And so these poles that Lovelace found correspond to the closed string particles that you find at one loop in this way. So this alpha 0 equal 1 d equal 26 critical string theory has an infinite algebra of symmetries operators, L sub n, m goes over all the integers. And these symmetry operators are crucial for eliminating states with which would have negative norms, which is sort of like negative probabilities. And so the existence of these infinite algebra of symmetries is absolutely crucial for getting a sensible spectrum, in the sense that there are no ghosts with negative probability. So 2 different proofs of the no-ghost theorem were found by Brouwer on the one hand and Goddard and Thorne on the other in 1972. So that was an important development too. Now in January of 1971, Pierre Ramon introduced a string theory analog of the Dirac equation, where as you probably know, is the relativistic wave equation for the electron. His proposal was that just as the string's momentum p mu can be viewed as the zero mode of a string density capital P of sigma, the Dirac matrices gamma mu should be viewed also as the zero modes of densities capital gamma of sigma. And so then he took the dot product, capital gamma dot P, and looked at all its Fourier modes in the usual way. And in particular, f sub 0 would give you the ordinary Dirac operator, gamma dot P, plus a bunch of other terms involving the oscillators associated with the non-zero modes of gamma and P. So the analog of the Dirac equation in this notation takes this very simple form. So I like to call this the Dirac-Ramond equation. And he observed that the Virasoro algebra generalizes to a super Virasoro algebra that has odd elements f sub n in addition to the even elements ln that I mentioned earlier that generate the Virasoro algebra. The f's sub odd means they're fermionic. And if you want to combine two of them, instead of having a commutator, you have an anti-commutator. The anti-commutator of two f's gives you an L in particular. So in March 1971, a couple months later, Andre Neveu and I introduced a second interacting bosonic string theory. And it's similar to the Ramon's fermionic theory, but the periodic density gamma mu of sigma is replaced by an anti-periodic one, which we called H. So here's the statement, what I mean by anti-periodic. So together with Charles Thorne, we showed next that the bosons that Neveu and I found and Ramon's fermions actually combine into a unified theory of bosons and fermions. And this was an early version of superstring theory, but there was much that still remained to be understood. I showed that the space-time dimension of the critical RNS string, by an analysis analogous to that of Lovelace, is 10 dimensions. So instead of 26 dimensions now, our second theory requires 10 dimensions. Goddard and Thorne independently showed that D equal 10 is the critical dimension for this theory. So my thinking at the time was that this is a step in the right direction, and maybe our next theory will have D equal 4. But that's not how the history played out. Later in 1971, Gervais and Sekita constructed a two-dimensional world sheet action for the string where the x's are just the bosonic coordinates, and then in the superstring we have the fermionic coordinate psi mu. And so this is sort of like a Dirac term, and this is sort of like a scalar term in a field theory. And they observed that this action has a symmetry where the x's can be rotated into size and the size can be rotated into x. It uses a fermionic symmetry. So this was actually the first explicit example in the literature of a theory with supersymmetry. And so here this is supersymmetry in 2 dimensions, relating the bosons x mu and the fermion psi mu. So this is the beginning of supersymmetry. So this result motivated Wesson Zumino to construct 4-dimensional interacting supersymmetric field theories in 1973 and 74. And their work inspired the construction of possible supersymmetric extensions of the standard model. And that led to subsequent experimental searches at the LHC for supersymmetry particles, none of which have been discovered so far. Presumably they exist, but they're heavier than where the machine can probe so far. They might be very much heavier, in which case we'll never find them. I don't know. It makes sense that they continue looking. So let me tell you about the decline of string theory. So the success of QCD in 1973 eliminated the need to formulate a theory of hadrons based on strings. Q2D was clearly the right theory. I knew it, everyone else knew it. String theory as a theory of hadrons had problems, an unrealistic dimension of space, 25 or 9, and the presence, which I didn't discuss earlier, of tachyons and massive particles. Tachyons are particles with negative mass squared, which means that which implies they would if you took them seriously, would be traveling faster than the speed of light. Of course, that's absurd, so they shouldn't be. Other exciting developments in this period, 73, 74, included the completion and acceptance of the Standard Model, as well as interest in studying supersymmetry, as I just mentioned, and grand unification, which is meant to relate the various forces that were known. And these were all very exciting topics. So it's not surprising, therefore, that string theory, which had been a thriving enterprise for several years, rapidly fell out of favor. The problem that it had set out to solve had been solved by a different method. End of story. Well, as it happens, as you know, I suppose, it's not the end of the story. Because starting in 1973, Yonea in Japan interpreted the massless spin 2 state in the closed string spectrum in either 26 or 10 dimensions as a graviton, dimension, of course. With this identification and a theorem due to Weinberg, it was easy to show that the string theory agrees with general relativity in these dimensions, at least at energy is low compared to the string scale. Similarly, the massless spin 1 states in the open string spectrum could be interpreted as gauge theory particles. This had been shown earlier by Naval and Schwarz. So in 1974, Schwarz spent a term at Caltech, collaborating with me, and we proposed to interpret string theory as a quantum theory of gravity unified with gauge theory forces. A potential, I don't like this phrase, but it's used a lot, the theory of everything, rather than as a theory of hadrons. And so it's hard to believe that this is more than 50 years ago. It doesn't feel that long. This new interpretation suggested that the string length scale is comparable to the Planck scale, which is 10 to the minus 33 centimeters, roughly, instead of the nuclear scale, which is roughly 10 to the minus 13 centimeters. So suddenly our strings shrank by 20 orders of magnitude, which is a rather dramatic rescaling, but the math was largely unaltered, which is fortunate. So at this time, I felt that I knew what I would be doing for the rest of my career, because I thought was pretty exciting, and that's pretty much the way things worked out. So this proposal had several obvious advantages. First of all, the existence of gravity is required by the theory. We didn't set out to build in gravity, it just happened to be there in these formulas. String theory has no ultraviolet divergences, which is a characteristic feature of ordinary quantum field theories. Sometimes these kinds of divergences can be handled by renormalization. That's the case in the Standard Model. And it's some theories that involve gravity. If you try to write down a quantum field theory for gravity, the ultraviolet divergences will not be renormalizable. They're too severe. So this is something that has gravity and it doesn't have ultraviolet divergences. So in a gravitational theory, extra dimensions can actually be a good thing. This was noted by Kaluza and Klein many years earlier, in the early part of the 20th century, quite shortly after Einstein's introduction of general relativity. The low energy 4D effective theory is determined by the details of the geometry of the compact extra dimensions. So that's an important thing. And in recent years, there's been a lot of work studying different possible geometries for the extra dimensions. The unification of gravity with forces described by Yang-Mills theories is automatic in this framework. So how was our proposal received? So Joelle and I spoke about our ideas at various conferences and seminars. Most people were polite and showed interest. And a few highly regarded scientists, such as Gilman and Zumino, stated that our proposal was potentially very important. Yet our work was largely ignored. Why? I believe the answer lies in the sociology of the profession at the time. Relativists who thought about black holes, the geometry of the universe, etc., had no use for quantum theory. It was far removed from anything of interest to them. Particle theorists who were interested in understanding phenomena that could be observed in current or future accelerators had no interest in gravity. There was a lot of interest in supersymmetry, but not in gravity. It was far removed from anything of interest to them. Now, both groups of scientists were correct in their opinions, of course, and therefore the two communities were completely disjoint. And a proposal that would bridge this gap had very few takers. It took a decade for this to change, but when it did, it happened very suddenly. So now let's talk about supersymmetry in 10 dimensions. In 1976, Liazzi, Shirk, and Olive proposed a projection of the RNS string spectrum, both for bosons and fermions, the GSO projection, that removed roughly half the states, including the tachyon. I didn't mention this earlier, but the spectrum that we had both in 26 dimensions and in 10 dimensions had one particle with negative mass squared. And such a particle would travel faster than the speed of light. It's a tachyon. So this GSO projection eliminates the tachyon from the spectrum, as well as lots of other things. And they showed that after the projection, the number of bosons and fermions is equal at every mass level. And this was compelling evidence for 10-dimensional space-time supersymmetry of the GSO projection, of the GSO projected theory. But it wasn't a proof. Just having an equal number of bosons and fermions doesn't mean that they're related by a symmetry. Supersymmetry is necessary for consistency because the spectrum contains a massless gravitino. And the gravitino is the gauge particle for supersymmetry, and that wouldn't make sense unless they were connected by a symmetry. So the 10-dimensional space-time supersymmetry proposed by GSO in 1976 is distinct from the two-dimensional world-sheet supersymmetry identified by Gervais and Tsuchida in 1971. They're completely different things, even though both of them are supersymmetries. And they're both relevant to what I've been talking about. So the GSO projection is required for consistency. It ensures that the theory has supersymmetry in 10-dimensional Minkowski spacetime. However, it is important to note that this symmetry can be broken when the extra dimensions are compactified. And how it's broken depends on the details of the geometry of the compact extra dimensions. So once you have the theory of gravity, it's perfectly sensible to imagine that some of the dimensions curled up to form some sort of compact space. The only requirement is that it be consistent with the equations of motion. But since you're dealing with a theory that has to do with the geometry of space-time, there are lots of possibilities. So in 1978, Herbert, Julian, and Shirk discovered a supergravity theory in 11 dimensions. So this is not a string theory. It just contains three fields. It's a field theory. So you have basically Einstein's graviton, except it's written in 11 dimensions, but it's the same kind of formula. And then the fields, which are the gauge fields for the supersymmetry of the gravitino fields. And to get everything straight, this theory needs a third field, which is a three-form tensor field. So A mu nu rho, which is the total antisymmetry, and has a four-form field strength. Now, this 11-dimensional supergravity they wrote down is a very beautiful theory. It's a brilliant observation of theirs, but being a quantum or being a field theory and not a string theory obviously has severe ultraviolet divergences. So even though it's a nice classical theory, you certainly cannot make quantum mechanical sense of it as it stands. So a good question was whether it might be a low energy approximation to a consistent quantum field. And this question was answered in the affirmative, but it took a long time because they did this in 1978, and the question was answered in 1995 by Adam Burton, who named the quantum theory M theory. So this 11-dimensional supergravity is just a low energy approximation to M theory. So in 1979, Michael Green and I began a collaboration, and the initial goal of our collaboration was to understand the 10-dimensional space-time supersymmetry of the GSO projected RNS string theory, and which we then named superstring theory. As I mentioned earlier, just having equal number of bosons and fermions doesn't mean it's supersymmetric. There have to be explicit transformations with all the right properties relating bosonic fields and the fermionic fields. So this was a challenging problem, and whenever we worked on that, so whenever possible, we also collaborated with Lars Spring. Now, Joel Scherk tragically died in May 1980. He was less than 40 years old at that time. Otherwise, he undoubtedly would have been a collaborator in the work that I'll be describing, and he would have been a major contributor. Green and I formulated what we call type 1, type 2A, and type 2B superstring theories. So we had this GSO projected 10-dimensional string theory, but there were a lot of details that hadn't been explained carefully. And when explained carefully, we realized it was really three different theories that we could get out of it, which we gave these three names. We proved the 10-dimensional space-time supersymmetry of the spectrum and interaction in each case. So the theories with a 2 in them rather than a 1 have twice as many supersymmetries. So the type 1 theory has one supersymmetry, which in 10 dimensions has a supersymmetry spinner in 10 dimensions and 16 components. So this is, in a sense, 16 supersymmetries, and that's the 32 in each of these two cases. 32 is always the maximum possible amount of supersymmetry in any dimension. We computed various tree and one-loop amplitudes and elucidated their properties. We formulated superstring field theory and the Lycombe gauge for two of the theories, the type 1 and type 2B. And we introduced a new worldsheet formalism that made the 10-dimensional space-time supersymmetry manifest. Okay, I'm running a little long, but I'm near the end. So, is it okay if I take 5 more minutes?
Yes, that's fine. Yes.
Okay.
Please.
So it's essential for the consistency of the quantum theory. The local symmetries, such as gauge symmetries and local Lorentz invariants of the tree-level classical theory, are not broken by quantum corrections. And such symmetry-destroying quantum corrections are called anomalies, and they potentially occur at one loop level in parity-violating theories. In other words, theories that are not invariant under mirror reflection. So the standard model is an excellent example of a parity-violating theory in which various such anomalies beautifully cancel. If one ignores the quarks or the leptons, the quantum theory would be inconsistent, but when both are included, their anomalies can cancel. So the standard model satisfies this requirement of anomaly cancellation. So the question is, what's going on in the case of string theory? So we had these three string theories, type 1, type 2A, 2B. Two more would be discovered the following year. So the type 2A theory is parity conserving, so there's no issue, and therefore it's anomaly free. However, the real world is parity violating, so it can't possibly be realistic. The type 2B theory is parity violating. And in 1983, Alvarez Gomez and Witten proved that all of its local gravitational anomalies cancel. And more recently, more subtle potential anomalies have also been shown to cancel. Anomalies whose existence we didn't even contemplate back in the 1980s. However, in 1983, it was unclear how one could get anything at all realistic out of this theory. That would change in 1996 when Vafa introduced a clever method to construct type 2B solutions that he named S-theory. So anyway, for these reasons, we focused our attention on the type 1 superstring theory. Classically, it's a parity violating theory, but it's defined for any orthogonal or symplectic gauge group. And there are two worldsheet topologies that contribute to the gauge anomalies. One is a cylinder, like we discussed earlier, and the other is a Möbius strip. So we discovered what Michael and I, by doing the explicit calculations, found is that the two contributions can cancel, but only if you choose the right gauge group. And that gauge group turned out to be SO32. So we had an infinite, up until that point, we had an arbitrary symplectic or orthogonal gauge group. And now out of those 2 times infinity possibilities, only one gave the anomaly cancellation. Any other choice gives a theory that is inconsistent at the quantum level. We confirmed this result by an analysis of the low energy effective field theory. And in this setting, we could also analyze gravitational and mixed anomalies. And it all worked beautifully for SO32. When I say SO32, that's a little imprecise. It's right, the algebra, if you want to be precise about the group, it's spin 32, mod Z2. We also discovered that the anomalies could cancel for a second gauge group, namely E8 times E8, which also has 496 dimensions in rank equal to 16. But we did not know a superstring theory with this gauge group. But it was plausible that one should exist, and we set out to find it. Within a few months, Gross, Harvey, Martinek, and Rome introduced the heterotic string for both gauge groups. So after 10 years on our own, we no longer had the luxury of working leisurely without worrying about the competition. The subjects had suddenly taken off, and following the anomaly cancellation result, and that may not be the E8 theory. Shortly after that, Dilworth, Strominger, and Witten introduced a specific type of compactification called, they named Calabi-Yau compactification for the 6 extra dimensions. And applied to the E8 times E8 heterotic string theory, they showed that this kind of compactification of the extra dimensions could give 4-dimensional theories with many realistic features. And in those days, one emphasized what worked, but nowadays I think it's better to emphasize what doesn't work. And well, they were clearly on the right track. We don't yet have anything that's exactly right. So let me conclude. The history of string theory is one of unification of particles and forces, of particles and theorists and relativists, of math and physics. It's been an exciting journey that's still going strong. There are several well-known examples of lucky experimental discoveries, but string theory is a very rare example of a lucky discovery in theoretical physics. Witten has remarked that string theory is the 21st century that happened to be discovered in the 20th century, which I thought was kind of a clever thing to say. The second superstring revolution occurred a decade after the first one in the mid-1990s. Important results concern new dualities, M theory, black hole entropy, F theory. I've alluded to some of these things already. Also, the ADS-CFT holographic duality discovered in 1997 was very important, but I didn't have time to try to do it. The current research directions include new types of symmetries, something called the Swampland program, celestial holography, a possible micron scale dark dimension. Let me conclude by saying that my current thinking is that cosmology might be a more fertile ground for experimental or an observational confirmation of string theory than particle physics. I've only come around to that point of view recently, but especially with the famous Hubble tension that you've heard about from Wendy Friedman, uh, I think that's that indication that that there's something fundamental to be explained, and string theory might be able to provide the way to do that. And I'm not, that's just speculation on my part. So let me conclude there. Thank you.
Thank you, Professor John. It was wonderful. It was amazing. It was like a very complete crash course in string theory, starting all the way from QED and QCD. I was making notes all the time. Point it was difficult to keep up, but it was really nice to know everything. The kinematics, relativity, you went all the way to then, the 26 dimensions, 10 dimensions, superstring, supersymmetry. I mean, I can keep going on, but I hope everyone was paying close attention to that. So thank you so much. It was really beautiful. I enjoyed the lecture very much myself, being a student of QED. It was really wonderful to hear this from yourself. So a quick reminder again for the participants, please, you can keep posting the question in the link that has been shared with you, so that we can, I will deliberate or ask the questions to Professor John Schwarz. I myself have multiple questions, but I will just take this privileged liberty to ask you, start with my question first. As you also beautifully concluded, I like the statement that the string theory is a theory of 21st century, which was discovered in 20th. So my question is, string theory achieves these remarkable theoretical consistencies and unification, but yet it lacks some direct experimental test. So what do you think in your view that what gives us confidence that we are on the right path, or do you see any potential experimental test in your future?
Yes. So there was a period when people were hopeful that supersymmetry particles would be discovered at the LHC, and that would give us useful hints that could guide us to a more detailed string theory. But there's nothing that we understand that says that the scale of supersymmetry breaking should be accessible at the LHC. Any possibility all the way up to the Planck scale is conceivable, and so it hasn't shown up experimentally, and I'm pessimistic that it will. So as I indicated at the very end of my talk, is that I'm becoming more the that that string theory might be able to make some significant contribution to cosmology. I'm not the first person to say this. There are people working on this, and it's the famous Hubble tension, where the work of Wendy Friedman and her friends gives one value, and the study of the CMB gives a different value. The For the Hubble constant, it's a strong indication that the cosmological constant is a constant. It's evolving, and so it hasn't been done, but it seems possible to me. One could find a string theory framework in which one can just figure out how the cosmological constant should vary, how it should be non-constant, and perhaps be enlightening.
Yeah.
That's just speculation. That could be wrong, of course.
Yeah, thank you so much for answering that beautifully. So I'd like to take some questions from our participants, maybe a few of them, because we don't have much time. But okay, So the first question is, what kind of discrete symmetries one can expect to be spontaneously broken in the early universe as per string theory? Does string theory has any criteria like renormalization for any kind of loop calculation? So there are three questions actually. There are a lot. Maybe you could just choose which one to answer. And the third one is, under which continuous symmetry can be expected, which can unify gravity with other interactions?
Mhm. So anything involving cosmology, even though I'm keen to learn more about it, I don't feel confident to say more about. So I don't really feel qualified to answer the third question. And so string theory does not have ultraviolet divergences, so you don't need renormalization. So the loops always different higher loop amplitudes have regions where the integrals converge. Uh, and so there's no renormalization involved. So that's it. That's a interesting fact.
Yes, thank you. Maybe we can take another question. Can you go to next? Yeah, okay, yeah. So there's a question from Sumit Tiwari, who is from Indian Institute of Technology, Bhubaneswar. He's asking, if you were a graduate student starting your physics career today, would you still choose
Yeah.
to focus on string theory, or is there another unsolved problem in physics that you would equally find compelling?
Right. So as you know, I didn't start out with the idea of doing string theory. It's just through the sequence of events that I described, that's where I landed. Uh, the there's no doubt that string theory is going to be around for a long time, but it's completely unclear how long it'll take to connect it up to the real world in a convincing way. That could happen tomorrow, and it could take many decades. Uh, so, I don't feel particularly qualified to tell other people what they should do. I think you should figure
Definitely.
that out by
Yeah.
yourself.
I think they're more interested in knowing if there is some, some unsolved big problem that you see that might be
Well, I
potentially.
mentioned these issues in cosmology that seem interesting to me right now.
Mhm. Yeah. Thank you.
One
Maybe
thing I didn't talk
post.
about, although I alluded to it, is this dark dimension. So an idea due to
Mhm.
Vafa at Harvard, and I think that's extremely interesting too. But I didn't have time to describe it.
Yeah. Thank you. There's a question from Rajesh, who's a consultant and learning mate. He says, you mentioned that string theory necessarily incorporates gravity. Could you elaborate on what makes gravity emerge so naturally in this framework, unlike other quantum field
Yeah,
theories?
right. Uh, yeah, we didn't set out to do it. We were trying to, as I told you, we were trying to describe a strong nuclear force, and boom, it was there. So it was this crazy thing that Lovelace discovered when we had this cylinder diagram, which had which we were thinking of as a one loop open string amplitude, but it became, you have this open string closed string duality where that same diagram can be viewed as a closed string going from one boundary to the other. And that's the closed string is the one whose modes including graviton. So so just by starting with a theory of things that weren't gravity, we found the theory has gravity. So we were particle physicists, we weren't relativists, and so that was just forced on us by the math. It wasn't what we
Mhm.
set out to do.
Yes. Thank you. Um, Maybe then I go to next question. The next question is from Dr. Roshan. It says, before Lovelace's result, no one seriously considered dimensions beyond 4. What was the reaction in the community when 26 dimensions became unavoidable?
Yeah.
Was there any resistance?
Well, I mean, clearly it was unrealistic, and, uh, uh, and, uh, 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 I mean, I think my feeling at the time was this is a nice kind of theory. Maybe there's one for which you get 4 dimensions. Uh, and so we tried to get another theory that turned out to have 10 dimensions. And as I said, at that time, I was saying, well, maybe our next theory will have 4 dimensions. But right now, after all these years, there aren't other string theories found. I mean, there are details about the theories I described, which can be called different sub-theories, but basically I described the basic kinds of theories that there are. Uh, so the thing is that when you make a quantum theory of strings, you get gravity whether or not you want to.
Yes. Yeah, thank you. Maybe we just take one last question, keeping in mind the time. So we have many questions coming, but we can, yeah, just take one more. Question from Ruthvik. He says, string theory initially lost relevance after the success of QCD, but later re-emerged as a framework for quantum gravity and unification. Looking back, what do you think allowed string theory to survive that period? And what lesson does that hold for how we evaluate new theoretical ideas today?
Yeah, I mean, that was certainly one of the themes of what I was trying to convey. That in 1974, Shirk and I realized that even though we'd set out to describe the strong nuclear force, we had a theory of gravity. And so we don't need, and we don't need a new theory of the strong nuclear force because we've already got QCD, which is perfectly fine. So we could have done what most people did, which is go work on QCD and the other topics I mentioned, or take string theory seriously, but that means talking about gravity because that's what it gives.
Wonderful. Thank you so much, Professor Jones. It was really remarkable, very inspiring, and very good to hear all this from you directly. Because in regard of limited time, we would like to stop our Q&A session here. But we really appreciate you joining us and deliberating this lecture at your time. And thank you so much for joining. And I'd also like to thank the Jigyasa group from IIT Bhubaneswar and NICER, who are actually live streaming the event also there to the students in the university. So thank you. And thanks a lot. So moving ahead, so now we have our second lecture of today, which is titled Bubbles and Voids versus Fancies, from David Dilworth, who is formerly a US Naval postgraduate from Postgraduate School, USA. So it is very interesting lecture, so I'd like to request everyone to please continue being with us. Before that, again, a very quick announcement. You can scan the QR code. The link is shared with you in the chat to ask questions. You can ask question during the session, immediately after, and we will try to collect as a few of them because, again, because of time, we will collect a few of them, and then I'll ask them on your behalf to Mr. David afterwards. Well, a very quick introduction of David before we start with the lecture. David J. Dilworth studied cosmology at U.S. Naval Postgraduate School in Monterey, California, by invitation of Emeritus Professor Karl-Heinz Kai Wohler, who assisted his professor Werner Heisenberg. David humorously points out how this makes him Heisenberg's grand student. David's superpower is an ability to translate complex and obscure cosmology into plain English, which is possibly why his award-winning website, cosmologyscience.com, was ranked #1 in web searches for best cosmology blog for 10 years. David's goal in publishing his cosmology and philosophy work is to remind us of the minimum criteria for providing a claim which has scientific value, specifically the bright lines between hypothesis and conjecture, and separately distinguishing scientific theory from non-science claim. He's just finishing a paper solving philosophy of science's enigmatic demarcation problem, offering it for publication this year. Dilworth is a prominent figure in the alternative cosmology community and founder of science-based cosmology. His glossary of cosmology principles and cosmology hypothesis application form are useful and popular tools for cosmology students. Due to his extensive and detailed analysis of logical and observational anomalies, he questions many fundamental facets of Big Bang models, noting how primary supports such as universe expansion, cosmic microwave background radiation, and dark matter lack any direct empirical verification, require logical fallacies, or contradict bedrock physics. Dilworth advocates for avoidance of logical fallacies and a return to strictly empirically validated physical principles in cosmology, which leads to static, simmering universe explanation. So, with this, I would like to invite David Dilworth to deliver his lecture. The stage is yours now. You can turn on your microphone and the video.
Unmute. Is this better?
Yes, now I can hear you. Yes.
Good. And what I'm not familiar with the process of starting up a PowerPoint.
Okay.
Do I just I might need a little bit of tech support here.
Sure, I can try to help you. Did you open the PowerPoint in your computer?
Yeah, it's open right now.
Okay. So now if you are in this window where you can see me, you can go to the bottom. There might be some tabs and one of them says share.
Okay, share.
And if you click on that, then there will be multiple windows coming up. You can choose the PowerPoint.
Okay.
And then
oh, there we are. Share screen.
Yes, share screen, yes. And then you can choose which window or desktop to share and again confirm. Okay, I think we're there.
Okay.
I see your screen. I'm not sure if that's the PowerPoint, but if you
let's see,
open the PowerPoint. Yes.
Going now?
Okay, there's an animation that I see.
Yes, that's it.
Is it that one? Okay, and maybe you could also turn your video so participants could see you if that's possible. You have to go back to the Zoom and then there might be an option there.
Okay, I'm sorry, I'm not.
That's fine. That's completely fine.
Let's see what we got here. And obviously, I don't know what I'm doing here. I thought this was.
So do you have a second screen or is it this one? Okay. I mean, I think if it's good, if it's fine. I mean, we cannot see you, but we can hear you and your presentation is running.
Okay. Yep. You won't be able to see me thanks to a camera failure. Long as the video works, we'll be good.
Yes.
Okay, can you see this?
Yes, we can see the title screen, yes.
Okay, good. We're in good shape. So, good morning, Kolkata. I see it's nicely cool at your institute, and it's an honor and a delight to speak with you. I'm hoping to inspire you with my enthusiasm for cosmology. This is Kuipu, the largest structure in our universe that we've found so far. It's about 1.3 billion light years long. And here's my talk overview. I'm going to talk about unlimited inspiration, tempered by carefully limited hypotheses, not conjectures, and by using calm logic. Secondly, I'm going to talk about logical fallibilism, how my claims about science could be wrong, and so could anyone's. And which finally we'll end up with which leading models and theories try to explain our universe today. So first, we're going to embrace unlimited inspiration. And this is the deepest view we've ever had from the Hubble telescope. This was a point in space not far from anything known, but the telescope was pointed at a spot that was completely dark, unknown to have anything in it. And Hubble found tens of thousands of galaxies in this dark patch. Now, it did keep its camera shutter open for something like 11 days or 1,000,000 seconds, but this is what happened, from complete dark to filled with galaxies. And the brand new James Webb telescope has about the same resolution as the Hubble, but it has a different wavelength that it's sensitive to. It can see in the infrared. And so it gets much sharper resolution in some areas because it can see through dust, whereas the Hubble can see only in optical, like our eyes, and it's not quite as capable in some facilities. Once again, and you'll see this, I use it as a place marker between sections. You'll see Kuipu many times during this show. Once again, I wanted you to see the flying through. These are galaxies. They're not stars. 200,000 galaxies, thanks to the European Southern Observatory. This is not an artist's conception. Those are real 3D mapped galaxies. So as recently as 1974, we had only measured about 500 galaxies with redshift. That's not many. And up till the time Hubble was launched, we only had about 1,000 galaxies measured with redshift. It was a painstaking process. It had to be done with a telescope, essentially by hand. Hubble helped us jump from 1,000 galaxies to about 170 billion galaxies. Hubble didn't do it alone. There were loads of other galaxies and instruments available by then. And now the new James Webb telescope has increased the number of galaxies that we've actually measured redshift with to about 2 trillion. So it's been going up in leaps and bumps, but it may be slowing down a little bit. So you heard Wendy Friedman a little earlier in this conference, and she described how cosmology's near future is the golden era, where landmark discoveries are calling. The Sloan Digital Sky Survey puts out they collect about 200 gigabytes of data daily. The brand new Vera Rubin telescope in Chile generates 10 terabytes of data daily. And the European Southern Observatory, also in Chile, has a library of about 1.5 million images and 65 terabytes of data. What this means to beginning students is nobody is ever going to be able to deal with all that data. There's going to be so many treasures hidden in these terabytes and gigabytes and petabytes that you'll be able to come up with just about anything. It's like walking into a gold field and finding gold nuggets everywhere. There's just so much to be explored. And it's there for the taking. Next, I want to talk about logical fallibilism, how science sometimes gets off track. And the idea is that all scientific theories, interpretations, or explanations are not permanent. They're indefinite, provisional, or tentative. Unlike mathematic proofs, like the Pythagorean theorem, math proofs have finality. Once you come up with the Pythagorean theorem, it's never going to be improved. It's done. For the rest of civilization, it's solid. But physical science proofs, when we're observing things and coming up with ideas, they're never final. They're always subject to new evidence or reasoning. Now, that's not entirely true. There's a handful of exceptions, like the number of protons on a certain element. But small things with integers like that and the inverse square law, those are pretty solid. But when it comes to measuring things like redshift distance and the Hubble constant, these, as you will see, have grand differences in accuracy and new evidence coming up all the time. So the Hubble constant I just mentioned, that's how fast galaxies are supposedly receding from us. It's been measured many, many times. There are now 4 different teams as of this year that they've come up with widely differing measurements from 67 to 73. Yet all are strongly confident in their results. Each team swears up and down that theirs is the final answer, which leads us to this bumper sticker: cosmologists are often wrong, but never in doubt. So this is for all the students of India. Does this sound familiar? The beginning of all knowledge comes from humility. Does it ring any bells? It's from the founder of the Institute, Bhaktivedanta. I hope I'm pronouncing his name properly. This conference is to celebrate 50 years after he created the Institute. So here's my opinion. We need to foster a cosmology culture that's comfortable with uncertainty. My experience is that we need more uncertainty. Well, we have plenty of uncertainty, but we don't often state it when we're talking with the media or the public or between ourselves. So that's my opinion for today. Once again, Kui Poo, I want to keep reminding you of the largest structure in our universe. So this is the third section of my talk. What leading models and theories explain our universe? Well, I'm going to talk about it in 2 different major categories: size and time. Size relates to a static universe with no expansion, and change in size, which is expansion like Big Bang, or like Paul Steinhardt, who spoke a little earlier, he prefers a cyclical idea where the universe expands and contracts and expands and contracts. The second category is indefinite or infinite versus finite. Big Bang has an absolute finite finish to it and start. It has a finite start, excuse me. So here we are. I hope you can see my cursor here. So we're going to start with the indefinite time, which could be anywhere up to trillions of years. The first static universe descriptions were before history. People have always imagined that our universe was static. Thomas Digges in the 1500s was the first one to put it on paper. More recently, we've had Hilton Ratcliffe from South America. He wrote a book called The Static Universe. And Eric Lerner, who has a book called The Big Bang Never Happened, he talks often about the plasma universe, but he's also a supporter of a static universe. Einstein actually also first preferred a static universe until he was persuaded that his general relativity equation needed an amendment, and he called it the cosmological constant, and it's now part of Big Bang. So then when it comes to expanding or contracting, Big Bang, obviously, there's 20, few people understand this, but Big Bang has about 20 different variations. There's the standard variations like Lemaitre and LCDM, or um, uh, lambda cold dark matter, which is the most popular one, and the many cycles like Steinhardt describes. But what is not well known is that the steady state idea pushed by Burbage and Fred Hoyle, and the quasi steady state, also by Burbage, and the plasma universe by Alfvén, those are all expanding or contracting. Those are expanding issues. We have down here on the bottom, I just wanted to pop this in, non-science. The Bible has an idea of how the universe was created, and the multiverse is another one. But no, both of those don't fall into the category of science as much as some people would like them to be. Big Bang defined. So all the Big Bang models generally propose that all matter, energy, and forces were created instantly from a hot dot, smaller than an electron some 14 billion years ago, and expanded and cooled to what we now observe. Please note how electromagnetism was never involved. Matter of fact, we don't even know, I'll go back here, we don't even know what the supposed force was that caused a Big Bang. But no one has ever asserted that electromagnetism had any part in this. So you're quite familiar with this, I'm sure, that Big Bang theorists claim that 95% of the universe's matter is either undetected, unexplained, or unknown. And the known matter, we've only got about 5%. That's the visible things that you can see, like our sun and planets and asteroids and galaxies and so forth. So here's the general state. Expansion models like Big Bang, and then static models. And here's what I think is a pretty dramatic distinction between the two. Unobserved forces. Big Bang, yes, they've got unobserved forces. Unknown matter, right. Dark matter, unknown phenomena. Expansion, inflation, take your pick. Unknown energy. Yeah, we've got dark energy. And adjustable parameters. Big Bang has up to usually about 6, but up to 19 adjustable parameters. Sort of like a black box. You can adjust things to make the answers come out how you want. And we got one other one. This was an amusing thing from John's talk just a few minutes ago, where he talked about dark dimensions. That's a lovely new idea. I've also heard of dark magnetism, which I don't know how to incorporate into this, but stay tuned. Another very important thing is that the largest scale force in Big Bang is gravity. They assert that the largest scale matter and forces that influence the dynamics of our largest scale structure is gravity. Whereas in static models, the largest scale force is electromagnetism and not gravity. And we'll go back up. This adjustable parameters static models have no adjustable parameters, no unknown energy, no unknown phenomena, no unknown matter or forces. So Big Bang models need gravity not electromagnetism, because Big Bang is built upon general relativity's gravity equations. Some people are not familiar with the idea that general relativity is where Big Bang came from, and general relativity is a gravity principle. It's also not widely known that Big Bang expansion models are extremely controversial. So controversial, they've spawned plenty of debate in books, papers, and conferences. Some years ago, this prompted the formation of a growing worldwide group of hundreds of astrophysicists signing a paper called An Open Letter of Concern, and it was published by New Scientist magazine. I think that was in about 2006. And it's not just the people who are questioning Big Bang who are a fringe group. The most prominent cosmologist in the world just won the Physics Nobel Prize in 2019 for cosmology. His work on it is Professor James Peebles. And he said, we have empirical evidence that there is still better theory than LCDM, lambda cold dark matter, to be found. Still a better theory to be found. So supporters of Big Bang include Jim Peebles, Ned Wright, Joel Primack, who just died, I think about a month ago. He was from across the bay from me in Santa Cruz, California. Joel Primack was the guy who essentially was the author of the lambda cold dark matter model. So Big Bang has many basic flavors and 2 optional amendments. Inflation and the accelerating universe. The accelerating universe is the part that got a Nobel Prize on its own a few years ago. And the most popular of all of them is the LCDM. Qui-poo, one more. So I'm bringing you some good news. Dark matter has been found in 2 different ways. And then we're going to talk about how microwave background isn't, expansion's tricky requirements, and the most distant galaxies that we've been able to study have the same ratio of red to blue as nearby galaxies. Red to blue galaxies are old to new. And the large-scale structure of our universe is not circular or spherical. So in 1933, a fellow named Zwicky calculated that dark matter must exist when he was looking at the rotation curves of galaxies and clusters of galaxies. He calculated this using the virial theorem, which is a principle that relates the kinetic energy to the average potential energy of a stable system of particles. And he thought something was missing. So he's the one who came up with the idea that dark matter is there and it's missing. It's missing from all of our observations. However, the first group who actually found dark matter didn't find any physical object. What they found was that the galaxy rotation curves are fully explainable without any dark matter. Chuck Gallo, Charles Gallo, and James Feng, they published in 2003, and they published several articles since then. Sadly, Chuck Gallo also passed away not long ago. So here's here's the next search for dark matter, and I would like to say that it's over, and it's actually been found by the Docum and Conroy team. And it was staring us right in the face all along as ordinary. Admittedly, it was difficult to see, but we can all celebrate and then get back to work. So I'm going to start here with a question. What's the most common star type in our stellar neighborhood? I can't see any hands, but we'll assume you're leaping out of your chair to answer that. So what is our Milky Way galaxy's most common star type? And what type of star is our nearest neighbor? Red dwarfs. It's not those red dwarfs. Red dwarf stars. not the Disney dwarfs. Anyway, red dwarfs are the coldest, smallest, and the most common stars. Here you can see in this little picture, there's the upper left is a relative size. That's our sun. And next to it, that medium-sized object, that's a red dwarf star. Three little ones in the center, those are brown dwarf stars, which are smaller and colder yet. And finally, on the right, about the same size as the brown dwarfs, is Jupiter. So that gives you an idea of the temperature and the size the red dwarfs, brown dwarfs are to our sun and Jupiter. So gigantic amounts of missing matter were found hiding as very faint red dwarf stars. You saw because of their temperature, only 3,600 degrees Kelvin compared to our sun, which is almost double that. They're hard to see. In fact, Proxima Centauri is a red dwarf with a mass of about 10 to 12% of our suns. And in our own neighborhood, our nearest stars, including Proxima Centauri, there are almost as many red dwarf stars as there are all the other types of stars put together. That's kind of a stunning discovery. Once again, here's Kui-Poo. Now we're going to go talk about microwave background. Is it an illusion? What's not widely known is that microwave whole sky resolution is terrible. It's absurdly awful. Our best whole sky microwave data has 58 times worse detail resolution than Hubble. Does everybody know what resolution on a camera is? Well, the whole sky microwave cameras that we use, like Kobe and WMAP and Planck, some of them have better resolutions than the others, but none of them have as good a resolution as a good old camera that you've got on your kitchen table. And resolution is what tells us what the details are, where we can see stars at the center of our Milky Way galaxy, and we can see galaxies literally 11, 12 billion light years away from us. So our best whole sky microwave data is 58 times worse detail than Hubble. Actually, that's wrong. Our best whole sky microwave data is 58,000 times worse resolution. So we're going to talk a little bit more about that in a minute, but we're also going to combine that with explaining how foreground microwaves, it says date, I meant data, foreground microwave data is real, but background microwaves is not real. It's calculated. So the microwave foreground definition is where you have to start, because microwave foreground is subtracted from the whole sky data to come up with background. So foreground microwave radiation is defined as that which comes from known matter sources: stars, planets, dust, gases, galaxies, nebula, anything you can actually see as a physical object that's emitting microwaves. And it's physically verifiable. We can stick cameras up there, microwave cameras up in orbit, and aim it at an area, and we can get readings, literally pictures of microwave areas in our vicinity in almost any direction. We can't get it when we look at the sun. Actually, we can get it when we look at the sun. It's just overpowering. The idea is we can take photographs of foreground microwave radiation. So here is, I'm going to call this a false colored map of microwave radiation, but essentially every image you get, whether it's from Hubble or Webb or any of the microwave satellites, it's all false colored, because microwaves don't have a color. So we have to attribute colors to them to try to pull them apart. Well, here, the red-orange in this image is undisputed microwave foreground. All the red, orange, yellow is considered microwave foreground. And the reason is this is a whole sky image, and it's looking, the center of our Milky Way galaxy is that plane right through the middle of the image. And you notice that the microwave radiation is most intense right at the plane of our Milky Way. And it has flares and loops and whirls all over the place. The blue is what's calculated. It's leftover microwave, and we've been calling it background. So microwave background is defined as radiation not from known matter sources, stars, planets, dust, gases, and galaxies. But background is a calculation, not a picture. You cannot take a photograph of cosmic microwave background. We only arrive at it by subtraction. To get the microwave background map, we have to subtract completely arbitrary versions. Okay, they're not completely arbitrary, but they are, every team uses a different version of microwave foreground radiation, and you subtract that from the whole sky microwave map to get the background. Here's the same image as the previous one, but it's in the original colors right from the Planck ESA data set. And this time, instead of the colors are somewhat reversed. So the bluish white in the center, those are the microwaves, also along our galactic plane. And we're going to zoom in down towards in the lower right corner, towards the large Magellanic Cloud and the small Magellanic Cloud. And so you can see pretty clearly how the light blue, whitish areas are foreground microwaves, and how they're pretty distinct, how they always come from distinct sources, like the Large Magellanic Cloud, our nearby galactic neighbor, and the small one. So here's where we're going to look at the terrible resolution of the instruments that have been giving us microwave data for the last 40 years. On the left-hand side, these are the three main satellites that the United States, and the European Space Agency have put up. On the left is COBE, the original one that came up with the first data that essentially killed the steady state universe theory. The WMAP, which Wilkinson microwave anisotropy project, well, that had a much higher resolution. You can see how the resolution goes from very fuzzy on the left one to the middle one. It's fairly improved over the left one, and the Planck is a better resolution yet. But I want to give you an idea here with this picture how awful the resolution is, even with the best ones. So on the leftmost box, each one of these boxes are 10 degrees on a side. The leftmost box has a 7-degree square area outlined on it. And that is the size of COBE's pixel. A single pixel from a COBE image had a 7 degrees by 7 degrees square image. And in the upper right part of that little box is the moon depicted. The moon is only half a degree across. So you can see the comparison of the size of the moon to a single pixel of the COBE data. Sort of dramatic. You can see that when COBE took a picture and it included the moon, there was a whole lot of other space that was emitting microwaves. So also relative to this, everybody thinks, a little everybody, an awful lot of people I speak with talk about how they think microwave resolution is really pretty good. And they think it's about the same as Hubble. Well, at the distance of the moon, the Hubble resolution is about 100 meters. That means it can just make out objects that are 100 meters across. About, let's see, that's about 300, 100 meters is 100 yards roughly. But the moon's diameter is 3,500 kilometers. So that little red dot up there, that's 3,500 kilometers across. And the Hubble resolution is exquisitely much more detailed. So here's from NASA. COBE had an angular resolution of about 7 degrees across the sky, 14 times larger than the moon's apparent size. Remember, that's for a single pixel of a COBE image. This made COBE sensitive only to broad fluctuations of a large size. Well, that's an understatement, the size of Jupiter. So here's I hope it's an interesting comparison of the microwave satellite's resolution at moon distance. So if you're aiming the 4 satellites, Hubble, COBE, WMAP, and Planck, you're aiming them all at the moon. At that distance, what is the size of something, an object that you could make out? Well, Hubble could see something about 100 meters across. COBE could just make out something that was 25,000 kilometers across, 14 times the moon's diameter. WMAP, considerably better. We're down to 1,500 kilometers. That's actually less than the diameter of the moon for the first time. And Planck, we're talking 580 kilometers, still gigantically more than Hubble's image. So I expect that I've got the idea across right now that microwave satellites' resolution is absolutely terrible. I realize that is not why they were designed. They weren't designed for high resolution. They were designed to be highly sensitive to extremely faint temperature, the 2.74 degrees of the supposed background. But the problem is, when you have such lousy resolution, every single COBE pixel gathered the light from the whole 7 degrees times 7 degrees, 49 square degree field of view, and averaged all of it to give you a single data point. And that average included the microwave radiation from about 2.5 million galaxies. Every galaxy with hundreds of thousands, maybe millions of stars. Every Planck pixel includes the microwaves from about 50,000 galaxies. So every poor resolution, Planck, WMAP, and COBE includes the microwave radiation from tens of thousands to millions of galaxies and billions of stars baked in. That foreground radiation, the real foreground radiation, it's unseverable by calculation or any other way. The only way you can pull it apart is with higher resolution. And it's preposterously evidence-free to claim any of those satellites' pixel shows us non-foreground microwave radiation called background. Averaging microwaves means the foreground inherently affects your results. Every cosmic microwave background data point includes microwave radiation from tens of thousands to millions of galaxies. So no cosmic microwave background radiation maps have even 1 pixel without microwaves from thousands of galaxies. We can't measure places without galaxy clusters to observe background because we don't have any whole sky microwave cameras or sensors with sharp enough resolution that they can see between galaxies. We'd need sub-micro arc section sub-micro arc second resolution to be able to see those. So microwave background is an illusion. If your angular resolution is poor enough, every foreground microwave pixel is smeared and looks like background, even if every single microwave photon comes from a specific star, dust, or gas. Anything can be a UFO if you're bad enough at identifying things. Anything can be microwave background if you're bad enough at identifying things. So here's my opinion. It's all foreground. When our whole sky microwave satellite cameras get down to sub-arc second resolution, all cosmic microwaves will be identified as coming from matter, stars, dust, and gas, meaning it's all foreground microwaves. No matter how far distant it is, I believe that it's all going to be shown to be identifiable as coming from some discrete matter. Next, we're going to talk about expansion and redshift. I think maybe you all listened to Louis Marme's presentation on redshift. That he's really a remarkable researcher when it comes to redshift. There's nobody I know of who has got a better grasp of, I think he's identified something like 60 different redshift proposals and evaluated all of them. Anyway, I'm going to let him, I'll defer to him when it comes to redshift, but we're going to talk a little bit more about universe expansion right now. So all of the dozens of Big Bang models are based upon and require some 6 different concepts, including at least 2 conjectures, which mean they don't meet the minimum threshold for science. The first one, it's a real hypothesis, and that is that there's a spectral line redshift to distance correlation, which it is observed. We see that over and over again. And that's how we measure the distance to galaxies and stars. Although its data exhibits a large variance. Now, some people quibble about the large variance, but I would say that the variance with redshift to distance versus the spectral line, I'd say it varies about 10%. Although when you factor in quasars related to galaxies, the number is about 1,000 to 1. It's a gigantic variance. Anyway, that's a real hypothesis, and there is a real correlation between the spectral line redshift and distances. The second one is recession velocity. That's a hypothesis that the redshift distance correlation also means that most galaxies are rushing away from us. So the first one is distance. The second one is speed. And that is something that's never been independently verified. There's no other way to look at recession velocity unless somebody can come up with something clever. Because the recession velocity that is everyone like Wendy and her crew are arguing over, it's incredibly tiny. It's like millimeters per week. So, and it doesn't happen at small scales that we can get out there with a ruler. Anyway, recession velocity is something that we cannot verify. We only take it for granted that the redshift distance means that galaxies are rushing away from us. The third thing is expansion. This is the conjecture that the recession velocity from above requires that our universe is stretching, and that's called universe expansion. That's different than just moving away from us. The fourth one is extrapolation. That's a conjecture that I don't believe is a valid scientific hypothesis, that we can extrapolate backwards, that the purported universe expansion that we may be seeing right now extrapolate it backwards in time, 14 billion years, to a moment when all the matter and energy were packed together into a volume smaller than an electron. And the fifth one is universe expansion requires not the well-known and studied Doppler effect, but the relativistic Doppler effect. And there's only feeble, questionable experimental results with relativistic Doppler effect. It has been looked at in labs, but I'm not persuaded by the results. And the sixth one is universe expansion does not define or clarify exactly what about space is expanding. Is space a physical space that's expanding or an abstract space like an XYZ coordinate system? What is expanding? And if it's physically expanding, presumably semi-uniformly, how could we possibly measure that independently of redshift? What independent baseline inertial reference frame could we use? So here's a secret. Well, it's not exactly a secret. If you study cosmology, you'll come across it, but it's not well known, is that universe expansion does not occur on scales smaller than galaxy clusters. There's no expansion on our Milky Way, and there's definitely no expansion within our solar system. And because it doesn't happen at anything smaller than a galaxy cluster scale, there's no way we could ever verify it. So young and old galaxies have the same ratio of old to blue, or red to blue, young to old galaxies. So there's a researcher named Bomi Lee at University of Massachusetts, and they did some study on large galaxies at 11 billion years distance. And they found that large galaxies at that distance, which means they get away from the Malmquist effect, and they found that the old galaxies versus the young galaxies at the great distance had the same ratio as nearby ones. That means there's been no universe evolution. They studied something like 1,600, almost 1,700 galaxies, only 2.5 billion years after the purported Big Bang. And they had the same correlation of morphological properties and star formation properties as we see in the local present day universe. So that means there's no large scale galaxy evolution that Big Bang and expansion needs and predicts. So apparently our universe doesn't have expansion. Could it be static, not changing in size? The last thing we're going to look at in this is that large-scale structure is neither circular nor spherical. Gravity only makes disks and spheres. Only electromagnetism and plasma makes filaments and sheets. But the universe's largest scale structure is not even close to circular. Gravity making disks and spheres looks pretty familiar. And electromagnetism, lightning and plasma are lightning is plasma. And you notice how electromagnetism makes pretty obvious filaments. Above about a galaxy scale, only electromagnetism and plasma make filament, sheet, and void shapes. And that's a little section of Kui Poo once again, which is why I've been showing it to you the whole time. So Kui Poo, our largest structure, is it round, spherical, circular, or is it filamental, composed of filaments? By the way, these lines, these filaments collecting the large bright areas, these knots of galaxies, almost every data point in there is a galaxy cluster. It's not just a galaxy, but there's billions upon billions of galaxies in all of those filaments. So now we're going to talk about Big Bang and the elaborate nonsense. Big Bang models require undetected matter, forces, energy, and phenomena. Their models are all ambiguous. They lack adequately defined or unstable fundamental terms, sometimes charitably called dynamic or moving goalposts, employ a minimum of half a dozen, up to as many as 19 adjustable parameters. This is the chart we looked at earlier. Unknown matter, unobserved forces, unknown phenomena, unknown energy. And the largest scale force in Big Bang is gravity. In static universes, it's electromagnetism. So not everyone knows that Big Bang was pulled out of a hat by a Catholic priest named Lemaitre, who dressed it up with some obscure math called general relativity. So the question is, what's the difference between Big Bang and the Bible creation story? And the answer is duration. One of them takes a little bit longer. Yes, there's a bit of tongue-in-cheek with my presentation here. So I truly believe this part, which is, depending on Big Bang, is like using a Paris street map to climb Mount Everest. It's just wrong. You can put, this is from the wonderful governor of Texas, Ann Richards, who said you can put lipstick on a hog and call it Noreen, but it's still a pig. So I think Big Bang is a hilarious spoof. It's post-posthumous, way beyond the aftermath of anything pre-posthumous. And we should all be asking ourselves, is reality negotiable? Well, Superman might get ticketed for breaking the laws of physics. And here's a picture of a cop writing them up. So static universe models, I promised I'd talk about these. Static universe models have no expansion. By definition, they just stay roughly in one place. They aren't expanding. They may have movement, like I think have you heard from Sandra Faber yet? She's probably going to talk about the great attractor. And static universe models have no problem with having local galaxies moving towards a great attractor. They just don't have any overall expansion. Static models are just fine with redshift, meaning only a distance correlation, but they reject redshift, meaning galaxies are rushing away from us. Once more, and static models do not require undetected matter, forces, energy, or phenomena. They do not employ any adjustable parameters. It's not well known that Edwin Hubble never believed in the expanding universe conjecture, even though others have plastered his name all over it. Yes, he came up with the principle that redshift means distance, but the galaxies rushing away from us, he never bought into. André Assis has written about that extensively. He has a number of remarkable books. So here's a little ballad. For 40,000 fortnights, Ptolemy ruled the skies with his earth-centered universe until its overdue demise. Well, 500 years hereafter, I'm embarrassed to confess, cosmology still embraces mirages for another goofy mess. Gravitational expansion, a self-conflicting view, another earth-centered blunder, misled by a sexy clue. If space really has expansion, then why not our Milky Way? Bang's galactic contradictions, such tortured disarray. Microwave background with an odor of illusion. Can't be caught by cameras, so blinded by calculations, sell us a delusion. Could it be because Big Bangers prefer a flashy show, sheepishly using wrong maps, then confess what they don't know? Well, back in our static simmering universe, raise a glass and join our song, sharing hearty cheers all the light year long. thanks to European Southern Observatory for this wonderful fly through of galaxies. There is no end. And my favorite aphorism, shoot for the moon. Even if you miss, you'll be among stars. Thank you.
Perfect. Thank you so much, David. It was really wonderful, very interesting, very
Can you hear
enthusiastic,
me?
and yes, I can.
Okay.
It was really wonderful to hear the talk. It was. I hope everyone was very interested, and it was very captivating. I always remember now Kyupu, the largest structure of the
Right.
around. So I'll not forget that. So thank you so much for talking about the universe models, taking us a little bit deeper into the microwave background versus foreground. That was very clear to understand. And talking about resolutions, expansions, and redshift, showing the nice images. Really wonderful. Maybe we could try to fix your video so that now we can start with the Q&A. I will
Uh,
um, I will bring some questions from the participants. If you can
Okay.
stop sharing, let's see if one of us can just stop.
Do I
Okay.
press stop sharing?
Yeah, I think now you are out of the sharing. So if
Okay.
you're on your Zoom window, you can
Uh,
see a video icon next to the mute unmute. Or someone could also ask to turn on the video, right, from the
oh,
host
I
side.
you probably won't get a picture of me, which my girlfriend says is a good idea.
Mhm.
But my camera's not working properly.
Okay, okay, okay. Then I cannot do much. Okay. Nonetheless, thank you so much for this amazing talk. And now I will bring some questions from our participants to you. Maybe we can
Wonderful.
just keep the question on the screen. So, okay, the first question is from Kumar Ravi, who is from Swami Vivekananda University, Barrackpur, West Bengal. The question is, which major observational pillars of modern cosmology, such as the CMB, Hubble's law, cosmic acceleration, and phenomena for which dark matter is invoked, which of these are comparable with static cosmological models, and which observation decisively rule them out?
What was the last part of the question? Which are
So,
these applicable to static universe, and
yes,
which I missed that
which
part.
and which observations rule this out?
Oh, and which rule this out? Um,
Yes.
I have yet to come up with anything that rules out a static universe. But uh, the uh, the tired light is one thing that um, everybody is on uh, tenterhooks, walking around tenderly,
Mhm.
dealing with redshift and whether it means uh, uh, anything resembling tired light is going to be the biggest question, I think, to be answered in cosmology in the next few years.
Mhm.
But cosmic microwave background, as I think I've illustrated, I don't believe it exists. And I don't believe expansion exists either. And I think those will be borne out the more evidence that we get.
Okay, thank you so much.
Does that help?
The next question, yes, definitely. Thank you. Also, I mean, could you see that we're also displaying the question on the screen? If you can open your, like, the Zoom, you can also read it out from the screen. So I will bring the next question to you, which is from Rajesh. He says, can you tell how the dark matter has been observationally inferred? Can we detect CMB using a homemade experimental setup?
Let's see. I think that was two questions. The first
There are
one
two
about
questions. The first one is, can you tell how the dark matter has been observationally inferred?
Yes, it started with Fritz Zwicky looking at galaxy clusters, and then that quickly was backed up. I think it was Vera Rubin who found that galaxy rotation curves didn't make sense. And I'll try to give you so there's spiral galaxies spin looking like water about to go down a drain. And when you compare them to our solar system, in the solar system, the closer to the sun, the faster the orbit. And the farther out, the longer the orbit. So, for example, Mercury goes around the sun very, very quickly, and it takes us on Earth, well, an entire year, where I think Mercury's orbit's on the order of 90 days or so. And Saturn and Jupiter, Neptune, and so forth, they take many years to get around the sun. Well, with galaxies that are spiral galaxies that are rotating, it turns out that as you get further and further out, all of them are making one revolution at about the same time. It's almost as though they were connected with spokes, so that Jupiter and Neptune and Earth would all be going around the sun in 1 year. And that's called galaxy rotation curves. And I think it was Vera Rubin who discovered that. And those two observations, Zwicky with his virial theorem and Vera Rubin with her galaxy rotation curves, that's how the original hypothesis that dark matter was responsible for the rotation curves and the unusual speeds in galaxy clusters. I think that's the origin of dark matter. Well, we've been looking for it ever since. And people they've been looking at the very large objects like star size and larger. Maybe Betelgeuse type things. And they've also been looking at gas and dust and the very small, from WIMPs to machos. And every every time someone's done an experiment for the past 40 years, they've come up empty. They cannot find any particular object that fits until the recent discovery of all the stars, the red dwarf stars that make up a tremendous proportion of our local galaxy. Now, I don't know if anyone's done substantial calculations on any of that. I haven't done the calculations myself, but there's something for a grad student or a researcher to take on to see what the fit is. I think it's a close enough fit that it deserves a good look.
Thank you so much.
And there was a second part to the question.
Yes.
I'm sorry, I missed that.
The second part, it asks, can we detect the cosmic microwave background using a homemade setup, experimental setup?
I would say you can't detect it for a couple of reasons. Well, the primary one is you're in your backyard. You're going to be looking up through the atmosphere, and it's all essentially absorbed by the atmosphere. You have to get outside the atmosphere. Even you could, from your backyard, you could send up a balloon and maybe get up above enough atmosphere to do something like that. That could be a do-it-yourself project. But maybe a more fruitful way to do it would be to get the data which is sitting. There's COBE data, there's Wilkinson microwave data, there's Planck data, and analyze the data yourself. Several researchers have done some things like that, and they've come up with some useful answers. So that might be something you could consider.
Yeah. Thank you. Thank you so much for explaining this very clearly. So the next question I would like to present to you is from Pradeep, Kendriya Vidyalaya Sangathan. The question is, well, the first he says, thank you so much for such an enlightening and thought-provoking lecture. It has truly challenged the way I view the origins of our universe. While I have been reflecting on the traditional Big Bang model and Sir Roger Penrose's conformal cyclic cosmology, I find myself a bit of a crossroads. Given that the cosmic microwave background radiation is used as evidence to support both the singularity of a single beginning and the aeons of a repeating cycle, does the current data actually allow us to favor one over the other? Or have we reached a point where our current explanation leaves the ultimate origin of the cosmos an open mystery?
I'll go with the open mystery.
Sure.
I, as you probably gathered, I don't believe there is any such thing as microwave background. So anything that depends on that, I'm sorry, is kind of I don't think it has any validity.
Mhm. Thank you. If I could present your next question. So it's from Roshan. Question is, with the current explosion of observational data, do you think theory is lagging behind data, or are we overfitting models to match observations?
Both. Theories are I would say they're stuck in the 50s and 60s, and this may be a bit of an overstatement myself, but it seems a little bit like rearranging the deck chairs on the Titanic. There's so much that is being overturned almost on a daily basis. New data coming from the Webb telescope and from the Vera Rubin telescope and the Sloan Digital Sky Survey. The data is just it's an avalanche. I don't see how anybody, no one person could ever keep track of all the new discoveries, let alone the data. The papers are coming. How many papers were published in the past week on cosmology just related to the Vera Rubin telescope, or well, the Webb telescope? I mean, it's just bewildering how much new data we've got, and the things that are being shown to be get overturned. It's like cosmology needs its own magazine for all the new information that's coming out and new discoveries.
Yes, indeed. Thank you so much. So maybe I'll just take one last question, keeping the time in mind. So the last question is from Yogesh from Indian Institute of Technology, Bhubaneswar. He says, as observations have expanded from billions to potentially trillions of galaxies, how has this improved our understanding of large-scale structures like voids and bubbles? Have these structures become more clearly defined or more complex than we initially expected?
I think you've nailed it. It's become more complex. I think the biggest leap forward in understanding happened with the Valerie de la Parent, Margaret Geller, and John Hookra project for the Center of Astrophysics. In 1989, they mapped a couple of slices of our nearby universe in 3 dimensions. It was the first time we'd ever had really good 3-dimensional data. And Margaret, on her own, I think maybe with Smithsonian Institute, put together a video, which I have buried somewhere, but I don't think it's available anymore. But if anybody can find the video called "So Many Galaxies, So Little Time," it's what inspired me to get into cosmology. It it's like the little video I showed you from the ESO about flying through galaxies. It's very much like that. And it was such a stunning change where we could only vaguely speculate on what the 3D universe looked like. And all of a sudden, that team of three found three-dimensional structures. They found filaments, they found sheets and walls, and strikingly, they found the voids, large areas with no galaxies in them. It was just, to this day, it's still jaw-dropping to me. And yes, we've learned more since then. We've found things like Quipu and many other sheets and walls and filaments, but I think that original research that showed the three-dimensional vision of our universe, I think that's still the most spectacular advance, maybe in my opinion, since the beginning of modern cosmology. My hat is really off to those three. That was marvelous.
Yeah.
So, is it getting more complex? Yes, but I'd say we're only really adding to it. What the wonderful three with Valerie de la Parent, a French researcher, John Hooker, who has passed away, and Margaret, who just retired. What they came up with, I think, is the most significant thing in cosmology. And they came up with essentially the stuff that's been added to since then, but I don't know if if the new evidence of large scale structure has really changed that much from the 1989 1991 data.
Mhm. Thank you so much, David, and it was really wonderful. I mean, as also hear from the questions, everyone was very interested, excited, and just thought-provoking, forcing us to think a little bit differently. Thank you so much
Great.
for taking a time out, sharing this with us, and QPU, the largest structure. Thank you so much.
You're very
Um,
welcome.
so moving forward, so now we are at the final lecture of our session today, which is Cosmology and Consciousness, Search for a Complete Story of Our Universe. And our final speaker for today will be Varun Agarwal, Director of the Bhaktivedanta Institute, alumnus of IIT Kanpur. Once again, I'd like to quickly remind all of our participants, please post your question after the lecture so that also importantly during the lecture so we have enough time to collect them and present to our speaker. Thank you so much. A very brief introduction before I hand over to you, sir. Shri Varun Agarwal graduated from the prestigious Indian Institute of Technology, Kanpur, India, obtaining his BTech in aerospace engineering in 1999. He worked on a project of solar-powered aircraft and was ranked first in his entire department. However, his longing for something deeper about life, which always bothered him, finally culminated in meeting Dr. T.D. Singh, the founder director of the Bhaktivedanta Institute. Under his guidance, he began studying ancient Vedantic wisdom, dedicating himself completely for the cause of helping humanity. He is currently serving as the director of the Bhaktivedanta Institute, Kolkata, India. Besides his various involvement, he frequently travels across India and abroad and interacts with scientists and scholars all over the world. He is also the editor of Bhaktivedanta Institute reputed journal, Savigyana. So with this short introduction, I'd like to invite Sri Varun Agarwal ji to present his talk today. Sir.
Okay, thank you, Dipankar. Let me share the screen. You can see it?
Yes. Yes, sir.
Oh, okay. So happy to be here. Let's see. Okay. So happy to be here, and we had a very good speakers. I think last 5-6 days, uh, a lot of good wisdom flowing from all over the world. And today also we had a very good history of string theory in the morning. So, and tomorrow we'll have our dedicated day tomorrow for the universe in the light of our ancient Indian systems knowledge. So, a lot of good scholars will be speaking tomorrow. Professor Maranjan Sinha and Shriram and Professor Iyengar, I think. So from me today, it will be a very simple presentation. We are with just a very small, simple ideas to share. So let's see. Okay. So we are celebrating this 50 years of our institute, and so these are lectures are part of this celebrations. We started in 24, 3 years we are celebrating. So 24 we started, and we started with a lecture by Phillips, who gave a very nice lecture on science and spirituality. And then we had summer school on origin of information. And then we had a couple of more lectures by Vineland, Baldell. And then we had a conference, Science Visual Quest, where our Genzel, who is also a cosmologist from Germany, he also gave a very good lecture that time. And then we had a conference on consciousness and 24. And then last year we had a 1 week dedicated on quantum foundations. Very renowned scholars from around the world, they poured out their thoughts. And Anthony Liggett, who is no more now, he actually gave a lecture in the event. So it was a combination of physical and online. So back to our topic today. My topic, so basic idea is this. This is a summary that will small introduction, and then we'll look at a little bit into foundational questions in cosmology, and then just a brief idea of some of the cosmologists. So when I'm using cosmologist means astrophysicist also, astronomer also, because title becomes too long. And then what is the issue or incompleteness of our current story of universe? What we have is a very good story, but still looks incomplete. And then some ideas for our IKEA from Indian knowledge systems, our universe in the light of Indian knowledge system. This is a rough idea we'll be traversing in this presentation. So first, so of course, cosmology has been exciting, and our David with Dilworth was giving amazing, exciting things, and also previous speakers too. They showed us various pictures, and these days we are getting every day new pictures from James and from around so many. So it's becoming more and more exciting, surely. And of course, the numbers are very exciting because the stars in the these stars only in the observable universe, which we can observe theoretically. So it is like you can see the big number, 10 to the power 24, and then the numbers really are in cosmology are beyond the human imagination. So we have trillion galaxies. Even our one galaxy we difficult to cross over, Milky Way, and we have 2 trillion roughly galaxies, and they are increasing. They are daily increasing as more we are researching and more exploring, and we are, as one of the speaker was telling, when he started working in cosmology, it was only million. Today we have trillion. So, and then, and our the distances, they are also very amazing. So cosmology is really very mind-boggling all the time, and I hope that it will remain always amazing. And so these numbers are really bigger than the human imagination. And of course, besides out there are also very amazing concepts in cosmology, which we have been hearing, black holes. Scholars have really worked hard on that, the dark matter, dark energy, and there are many universes and then many dimensions today morning. So string theory. So these are concepts which really open up our mind. So amazing ideas and amazing field this is really. So it is really exciting, and my guess is that it will remain excited as long as humanity is there, because its depths may not be so easy to fathom completely. So some of the foundational questions in cosmology, just to have a quick look that these are very deep questions and they influence whatever we are doing in this area. So I have listed some 15, 20 of them. So first, of course, why this universe at all? The like Wigner said, means for unreasonable mathematics, unreasonable effectiveness of mathematics means we deserve or we, the gift of universe means why this universe at all actually we have, and why this universe, how this started. This is a question. Many theories, some of we have prominent Big Bang model, but then the others, plasma and others, scholars presented. And then how the universe will end, we have some theories, but question. And what is our role in this universe? Of course, besides my degrees and jobs, do I have really role beyond in this universe? And then can we ever have hope to understand the structure of this universe completely? So that's also interesting thing that can we fully understand the structure of this completely, quote unquote. So is there intelligence behind this cosmos? So that's a question. Some say for and some say for oppose. And is universe only physical? That is one of the question I will explore in this presentation, I think. And is there a mind in this universe like we all do have? That is also a question which we will touch upon in this. And then, does consciousness has any role in the structure and formation of galaxies, or is just a mechanical process, mechanistic process? Can we ever hope to understand the universe completely, of which we are part of? Because we ourselves are part, so is it possible really to understand fully? Are there other universes? So this is a question. Multiverse is a great proposal, and there are a lot of logic, but it's still like string theory. It still has a no experimental verification. And how many dimensions space has finally? So we have a lot of proposals from 3 to 4, from Newton to Einstein, and then 5, 6, 8, 11, 10, 11. So finally, how many dimensions space has? This is one of the important questions, because all your theories depend finally on the definition of space which you assume to begin with. So, and then can we ever fully understand the space? This is another deeper question, fully in quote unquote. And then what is time really? That is another big question, because time, you can change your watch, but you cannot stop time. Time is really, nobody can stop here in this existence, because whatever clocks change, everything you can change, but it will move on, time will move on. So what is time really is a big debatable question, and so many events every day happen around the world on this. And are there absolute space, absolute time beyond this universe, as some people propose? So these are some of the foundational questions, and they occupy us. I will not be covering, just one or two I will be touching on them. So before that, let me get into some of the cosmologists, astrophysicists, astronomers. I have not put all of them, couple of them, just to have show some of the ideas which are some of the things which are lesser known in public. General things, people, it is very famous. Kepler, we know, we gave Kepler's laws, and then Temple, then Whittaker. Interesting is that Whittaker, one of the British physicists, he wrote a book called Space and Spirit. Very interesting title. And then, of course, Lemaitre is the Belgian astronomer priest who postulated an expanding universe. And then these two I have made different color, Eddington and James Jeans, Arthur Eddington, James Jeans. I will touching upon them, a little bit upon theme. Of course, Fred Hoyle, he worked a lot on this. And of course, in recent times, Barrow and Harrison and Burnell is still there. And then so our India, Subramaniam Chandrasekhar, and also Narlikar. Many are there, just not have to lift. So some of them, why I'm listing some of them is very interesting that they wrote books which are lesser known. For example, this Eddington, he wrote a book called The Nature of Physical World. And this book is very amazing. In the beginning, it goes into cosmology and then implications of it. So I recommend that those who are seriously interested to read all of these books. This is a small request to all of you, because that will very deep insight they have put. And second book is The Mysterious Universe by James Jeans. And then, of course, Carl Sagan is popular, and we know him. And then Gingerich, and then Narlikar. This book is Jan Narlikar from India, famous cosmologist. His book is lesser known. The Indian Scientist from Vedic to Modern Times. So the Scientific Age is the book name. And then Fred Hoyle, The Intelligent Universe. And then this is another book by Eddington, Science and the Unseen World. And then our Chandrasekhar, Truth and Beauty. So these, how this exploration into cosmos led them to deeper aspects of life to ponder upon. That will be very interesting to go through some of these books. So I'll touch upon few ideas from them, and then we'll move into some of the challenges. So this is James Jean, and you might have studied during your studies Rayleigh-Jean's law, or it comes in many names. It comes in many forms in our stellar dynamics and many areas of space. Jean's instability, Jean's length, you might have come across. So from this book, the universe looks like more and more like a great thought rather than a great machine. So James Jeans, very renowned personality. Actually, he worked a lot. Earlier, he was working in the subatomic world, and then he moved to cosmology, and then started working in stars, how the formation of stars. So when he went deep inside, then he came to this. And what is the basic idea? He presented very simple, but one has to go into it deeply to understand. Idea was very simple, that we use mathematics to describe universe, right? So from Einstein relativity, which uses tensors, to string theory, which uses Kac-Moore algebras, all those. So we use mathematics to describe universe, and mathematics has a very deep connection with mind. So, hello, is everything okay? So mind, because there are things in mathematics which have no counterpart. For example, Heisenberg gave example infinity or imaginary numbers, for example. So we don't have any counterpart of imaginary numbers in the physical world or infinity. So mathematics has a deep, rather they say that mathematics is more a mental construct. So since universe is defined in terms of mathematical equations and mathematics has a deep connection with mind, so just why James said that universe is actually rooted in mind. Very simple way presenting, but it goes very deep. The Eddington, interestingly, we all know Einstein, but you know that Einstein gave a theoretical framework of GTR, general relativity. He gave equations, used mathematics, but the first person who verified experimentally is this Arthur Eddington. In 1999, they went for a solar eclipse in Brazil, I think, and they verified that the theory what Einstein predicted was good. So Eddington did a lot of work. He was very much interested in stars. What are these stars? And he gave a lot of models to calculate the density, temperature inside the stars. And so he actually inspired a lot of. So he wrote a couple of very good books. The two I showed you, Science and Unseen World and Nature of Physical World. Another is New Pathways in Science. So if you go through them, then it will be very interesting and inspiring. Let me give you a glimpse of his idea, just a very short idea. I was going through, these are not his words, but this is what you will find there. I'm putting, so just lack of time, I have put in my word, but you will get exactly same ideas there. So Eddington was saying that, this is my language, but idea of Eddington, that one may say that I'm just atoms and molecules or dust like in the stars, but one thing which makes me different from all the objects around me is that I'm curious. So this curiosity, but from where this curiosity is coming from, that's a question mark. So why I want to know or explore stars and galaxy out there? Why not this table and chairs around me are curious? Where this quality of being curious is rooted in me. So Eddington, he put a very good question that definitely there's some difference out there in me. And then of course symbols and meanings means now we have from his time to now we have done a lot of further progress, but same question still remains. And he used that same question like we talk in consciousness studies. He talked that in the terms of observational cosmology that okay, the rays and the infrared rays comes from the stars, enter my equipment, telescope, and then go to my eyes and then to brain. And finally, where do I start discerning meaning of it? Right? Where this meaning, the understanding point starts. So he's asking about the observation, where it converts to understanding about that in me, where this chain of communication of symbols finally ends and leads to the meaning. And who is giving meaning to this? And of course, in later he says that, and after all these observations and making a theory and getting successful, finally, who is that one who feels happiness? And of course, since I don't know how I am there in this cage of brain and symbols, but then there must be something more beyond me. So that beyond me is a higher thing. And even he goes further that this physical realm which we are exploring, this is very close to our ancient wisdom, that the physical realm which we are exploring, actually this is beneath that there is a mental and spiritual realm behind. So, and also he says very interesting point that we should remember that whatever we are doing using inference in modern cosmology is good and very good. You cannot go out to the stars and the different galaxies, but mostly you are using inference. But remember that before inference, you have something which you have direct experience, which is mind. Mind is the first and most direct thing in our experience. All else is remote inference. So I'll skip this and then Gingrich. Gingrich he was astronomer. He recently passed away. We had a good relationship with him, our institute. He was from Harvard, and we used to meet him many times, and a lot of discussion. This is the book he gifted us, God's Universe. And he very openly, he was actually earlier working in the history of science, and then he also got into this astronomy, and he established himself very, if you Google it, you will know Gingrich, very well established, that there's a Harvard observatory, he was in there. So just I believe that the book of scripture illuminate the pathway to God. So I believe that the book of nature, which is its astonishing details, the blade of grass, the conus or the resonance levels of carbon atom, also says a God of purpose and a God of design. And I think my belief makes me no less a scientist. So this is. And another man we had, another scholar which we had very close relationship is Alexander Wellington. He's in Tufts University. He's very old now. Actually, he was also supposed to give lecture here. And then because he's very old and health is not very good, uh, so he could not do that. So his idea was very simple. This is a book, Many Worlds in One. Many years ago, he gifted us this book. And when we met him first time, he expressed that, well, I have a lot of ideas which are very close to your Indian ancient spiritual traditions. So his idea was very simple, that the universe starts and expands, and then from we have a lot of universes, but starting and then expanding, and then again the small universe comes out from there, kind of. And then he expresses that some kind of quantum tunneling happens. But the point he was making was that, like, you will get out here is this: the entire internally inflating space-time originated as a minuscule closed universe. It tunneled quantum mechanically out of nothing and immediately plunged into never-ending fury of inflation. Thus, the universe is eternal, but it did have a beginning. Means from one universe and then another, like this. But the question here is, the tunneling process is governed by the same fundamental laws that describe the subsequent evolution of the universe. It follows that the laws should be there even prior to the universe itself. Means Does this mean that the laws are not mere descriptions of reality and can have an independent existence of their own? And especially when in the absence of space, time and matter, then which tablets only they could be written upon? The laws are expressed in form of mathematical equations. If the medium of mathematics is mind, does this mean that the mind should predate the universe? So very, very logical, profound conclusion. These scholars, when they go deep, they come to this point that if laws are there before, and the same laws are continuing, then and we know the laws are written in mathematical language that and mathematics has close connection with mind. So does that mean that there's a mind which predate the universe? And this is our Indian famous cosmologist J.N. Narlikar from his lesser known book, The Science Age, the Indian scientist from Vedic to modern times. I request that we should go through this book, and he expresses many interesting things in this book. Most science religions are guided by man's search for truth, and the questions related to the working of human mind, its feelings, emotions, and the urge to know why is the man created, why are so many living species of different sorts in existence, what is the purpose of this creation, why are there laws of science in the first place, why do the laws discovered by man on this tiny earth seem to work on much grander scales of stars and galaxies? So these are important questions. These questions about cosmic truth seem beyond the scope of our current science, and this is where religion steps in. So these are some, just to give you idea that these interesting scholars, so that you can explore yourself more and more. Let me go to our current story of universe. What are the issues, the incompleteness where we face in this? Let me share with you. So there are 10 issues I am listed here. Quantum gravity means we try to bring together quantum mechanics and GTR, the whatever we have, general theory of relativity, and but there are foundation issues in quantum mechanics. So we'll very briefly look into then origin and completeness of laws. So these are the questions whether laws which we have, as we discussed earlier, are they, what is the origin, and also whether they are complete, means sufficient enough, what the laws we have discovered. Then incompleteness of mathematics itself, because we'll discuss little bit. And then where do new ideas comes from if the universe is only physical? How come we have fine-tuning order in the universe? You have heard a lot yesterday about it, so I will not go in detail about that fine-tuning aspect. Incompleteness of concepts in physics is a critical deep aspect which Heisenberg had mentioned, and which has deep implications. So can we build a picture of universe without including our own experience? Very important, because we have experience. The content may vary, but the experience is truth. So we have all experience. So can we build a picture of universe without including experience in that? That's the question. And of course, can we afford a meaningless life? Can we account for issues of morality and responsibility with the current picture of universe? That is, which is very important for any humanity to live on. And then of course you can even go to the climate and environmental issues. Can we ignore mind as in the current picture of cosmology and still hope for a sustainable future of our planet? So I'll briefly explain what do I mean by all these things, and not all, but some of those. So foundation in quantum mechanics is basically there are 5 major issues: the wave nature of matter, non-locality, measurement problem, uncertainty, and meaning of wave function. I will not be covering all, just briefly mention 2 of them. One is non-locality, another is measurement problem, these 2. Non-locality, as we know, entanglement means, or different names are there: action at a distance, spooky action at distance, Einstein called. So 2 particles at very far away, one here, one at the moon. So you change the state of one particle, the state of other particle changes, and that entanglement and speed of light, it cannot happen like that. It requires minimum time for here to go to moon, right? So, or any space, very distant space. So but it happens instantaneously. So how that happens is a mystery actually, and this was not believed. Then experiments were performed again and again, and then there was a question whether the experiment had loopholes. Then now recently the very good experiment was performed in last 20 years, 30 years or so, and then Allen aspect and all, they got Nobel Prize a couple of years ago, and then it is very clear. And now not only we are clear, we are using this property to make quantum computers. So though we don't understand how it is happening, we are using and encashing upon this property, and this has a lot of implication, philosophical implication besides technology. The philosophical implications is that whether there is a reality or underlying connection of things beyond the level of beyond space-time fabric. So how things are happening instantaneously, which cannot. So one of the implication is whether is there a connection between there's a fabric of reality beyond below space and time, beneath the space and time fabric, and because of that there is a connection. So what is that fabric then? And then that's why issues of mind, consciousness come into play. But basically, it raises question of non-physical reality fabric. The second is measurement problem, which we know that in a simple language, that how different possibilities are reduced to one. So that by the observation or by the measurement. So to put it in a simple language, imagine a boy or you met one scientist, for example, who was 90 years old, and at that time in New York, for example, and then you came to home to India, and then after 10 years you're thinking, I want to meet that scientist, but then immediately question comes whether he is alive or dead. He was already 90 at that time. So when a question comes in your mind, now you have both the possibilities, alive also and dead also. But in physical world, only one possibility can exist. Either he will be alive or dead. So the question is where, so same like this, the cat alive and dead. So question is where these possibilities are existing. If because our brain is in the physical world, and in physical world, this possibility cannot exist simultaneously. So then where these possibilities are existing. So this paradox, technically called Schrödinger paradox, also very easy to explain measurement problem. So then it brings the question of mind, and also the question of consciousness, means finally who decides which one is the correct, how you make a decision or like those. So these are some of the things which are foundational issues in quantum physics. And if you want to connect quantum physics with relativity, is not going to be easy job, and this is one of the challenges which comes. So that's why the story still looks incomplete. And of course, the second part I was telling you that the mathematics, which is like indispensable to explain universe out there, because we cannot go out to the other galaxies, and there are a lot of limitation of physical experiments. So mathematics is a great tool which we use. But at the same time, in the roots, mathematics has a limitation, like with our Gödel, famous Gödel's incompleteness theorems, 1931, that without mind and consciousness, mathematics is incomplete. Gödel himself said that my theorems only show that the mechanization of mathematics, that is the elimination of mind and of abstract entities, is impossible if one wants to have a satisfactory foundation system of mathematics. So when that means it brings a fundamental limitation to our model of universe, that the story of universe, whatever you have to say, that definitely it will not be complete or requires more. Eventually, if you want a complete story of universe, it will require perhaps mind consciousness to bring in. And of course, the question of intuition, this has, like, for example, Einstein said that the happiest thought when he was sitting in the chair and at his patent office in Bern. So Einstein called me that time he realized that if person falls, the first idea of the relativity he got, that if person falls himself, not the ball, so whether he will feel that weight, his own weight. So he will not feel his own weight. From there, he worked for next couple of years, 7-8 years, and so this intuition part, the intuition which is a essential part in our exploration. So how to account for that in our story of universe? So a lot of scientists worked on that. Actually, if you go deeply, Pauli, the physicist, he worked a lot on intuition, and then Poincaré, the French mathematician, he worked a lot, and then Brouwer even developed the field called intuitionism in mathematics, and Gödel made it very clear that without intuition or without mind, mathematics is actually incomplete. So this intuition is another important area to be entered inside our story. Yeah, our colleague said actually that how to account for the greatest gains of science quite often take place in an unscientific quote unquote manner, while feelings, intuitions, impulses, sudden flash of inspiration, even via dreams and visions. If you see the history of the discoveries either in cosmology or in other sciences, you see that how intuition plays such a profound role, but this is still not part of our equations which we have or the story which we have. And our Jacob put it very strongly, the day science and night science, that logical science of creativity, which we show to the public, and night science, the intuition part of creativity, which we don't so put inside. So fine tuning order, I think this part already was discussed a lot. I will skip this thing a lot, but just to tell you one interesting aspect, I think some scholar was mentioning earlier we met, that you see, if you little bit contemplate, it's not a question of any very simple question that, see, we are dependent on sun because you need sun rays for photosynthesis, right? And all your plants, vegetation depends on sunlight. So without that, you cannot expect life here. And now sun is a specific distance from Earth. And if that distance is little more or if it is less, there is a problem. If it is more, then you will not have sufficient sunlight. If it is less, then Earth will burn away. And not only sun, if you see, the sun itself is at specific distance from other planets, other galaxies. So that if that distance is also not proper, then that also will make the things worst. So idea is that learning gratitude, how we are dependent on entire universe. So when you take an apple which is made from the tree, which is dependent on earth and then on the sun, and then sun is dependent on all the other bodies in the universe without proper distances and movements and forces of gravity. So you can imagine that when you eat an apple, actually we should be grateful to the entire universe without that you will not get apple in your hand. And that's why our Fred Hoyle, he wrote a very interesting book, The Intelligent Universe, that if you go deep enough, he was talking about specifically about a carbon atom, because carbon is a very important atom in the universe formation. So a common sense interpretation of the fact says that a super intellect has monkeyed with physics as well as with the chemistry and biology, and that there are no blind forces worth speaking about in nature. So not only the story of universe is as a fundamental this conceptual issues, also it is related to our current things crisis which we are facing, mental health. One of the biggest challenges, especially in modern times, young generation, the issue of mental health and relationships. Very quickly relationship is making and breaking, and lot of mental health issues, depression, anxiety. So how our story of universe is connected, because if the universe is just the rock and salts and the stones and minerals without any mind, emotion, relationships, then our mind, it leads to a mindset, use fellow beings for your own pleasure and maximize own happiness without caring for others. No gratitude, no compassion. It's just a dead matter. So that breaks down the mind and the relationships. So that story of universe need to include the mind, so that it improves our mind, improves our relationships. The story is very, very important. And not only that, we recently met a physicist who turned from physics to sustainability into climate change. Also, Stephen Chu, who moved from physics in Stanford, who moved from physics to climate. So people are worried that today climate change is not just that you can manage by solar power and all, but actually it is rooted in mind change. So the mindset we have. So the picture of universe with the same pictures, rocks, salts, and then which leads to picture of earth, which is just rocks and stones. Then what is the mindset? Use and extract minerals, oils for advancement, as opposed to respect and use with care, as in ancient traditions. Like we used to teach in, especially in India, like Mother Earth, we use, but at the same time we have a lot of respect and care. So not to overuse, misuse the resources. So that mindset is also comes from the story of our universe. So that which leads to the planet crisis which we are facing, ecological crisis, climate crisis. So if you are not careful in using our resources and you are not careful in relationship with fellow beings, with other species as well as with the planet, then these crises are evident which we are facing today. So this relates to the story of the universe. And of course, the origin and completeness of laws, from where these laws, as I already discussed, from Alexander Wellington, and whether the laws are complete. Like Penrose was saying, that we have consciousness, but still consciousness we don't have in our laws. So that means somewhere something is missing. There is nothing in our physical theory of which the universe is like, what the universe is like. Though universe has elements, life, which has consciousness, but our theories still don't have that aspect. So these, and then let me share you briefly about the universe, some ideas, insights about the universe in the light of Indian knowledge systems, very shortly. I will cover briefly the nature of universe, the nature of life, the nature of mind, nature of consciousness, nature of concepts in physics, and story of universe in the light of Indian knowledge systems. Very simple way. So in our Indian knowledge systems, our tradition, the universe is not just the physical universe. Universe is actually, there's a physical universe part, there's a psychological universe part, and there's a spiritual universe part. So today, modern cosmology is mostly focused on physical cosmology, the physical universe. So the psychology universe means not only we have our own individual mind, it says there's also an element of mind in the universe. Means like you have this body, the hard touch, you can touch and see, and you can touch and see the earth, right, which is part of the universe. Similarly, not only you have mind, different from this physical structure called brain, which you can touch and see, in Sanskrit called mana, there is also mind element in the universe. So like that, other elements too. Similarly, not only we have consciousness, there is a consciousness at the root fabric of this universe. Like we have consciousness which we decides and take action. So it looks like, if you see from the light of IKS, Indian Knowledge System, our current view need to be expanded more. Similarly, the nature of life. Life is not just the physical body which I touch and take care of its nutrition. You also take care of the psychological aspect, the mind, the mental health, which is slowly, the awareness is increasing now these days. And then the positivity, the thought process, the peacefulness, the focus, all those aspects. And then it's the consciousness. So if we try to reduce, which has been the case in modern sciences, actually last couple of centuries, try to reduce life to physical structure, the brain, then you get a lot of issues. So the issues are this. The origin of life problem, you cannot make from, if I give you test tubes, chemicals in the test tubes, and you can make a living cell. We are trying protocell to this cell to that is going on. We had a whole event on the origin of life research a couple of years ago, I think. So that's and then issue conscious, very prominent, free will, the issue of purpose, issue of meaning. How do I meaning? Meaning, that is not on paper. Meaning is somewhere here. The issue of responsibility, if I do some action, who is finally responsible? If these are just carbon, hydrogen, nitrogen, oxygen atoms, this DNA, who is finally responsible in this body? The issue of intelligence, the issue of understanding, which I briefly mentioned, issue of numbering comes in mathematics, issue of gratitude, compassion, memory. We had a whole event on memory 1 or 2 years ago. Issue of happiness, which I think my colleague was there now covered yesterday. So these issues of life, they are not solvable with the physical definition of life. That if we try to reduce life to just the brain or DNA, it will not work. So that's why more and more scholars these days, either physicists, biology, or psychologists, they are coming with the things that we should get rid of this reductionism ideas which we have been maintaining in modern science from last 4 or 5 centuries. Now it's enough. Like Behe, Age of Evolution, irreducible is another physicist, Federico Fagin. He is the one who discovered first microprocessor. He's Italian, now in America. We meet him couple of times. Irreducible. You cannot reduce life or mind to matter. And then there's another psychology, irreducible mind. So our proposal is that mind is certainly not a classical object. The brain is a classical object which you can touch and see, but mind is not a classical object. It is more quantum-like object. Regarding the nature of consciousness in our Indian systems is that there are two types of consciousness. Like I'm conscious that this event is going on right now, and there's infinite consciousness, which we talk the consciousness at the fundamental root of this universe, and then whole the process goes our relationship between my and that the one who behind this cosmos. Nature of observer, yes, there's a interesting point here that, for example, in the morning, 8 o'clock, you're at the door and you have many possibilities in your mind that I can go to library, I can go to class, I can go to friend or restaurant or cinema. So all these possibilities are simultaneously not possible in the physical world, but they are simultaneous in your mind. So where are these possibilities, first of all? Because physical world, you cannot be at all the places at the same time. So definitely the mind. And then one important point is among all these possibilities coming to your mind, you select one. So the question is that who is selecting among these possibilities in mind, the thoughts? Thought 1, thought 2, thought 3, thought 4, T1, T2, T3, T4, T5, for example. Then, so this is different from India to Western tradition. Western tradition, mind, consciousness, they are all considered same. But our Indian tradition, the person, the being who is selecting among these thoughts is actually above, different from this. So that is called observer. And then behind that, finally, the supreme observer or supreme consciousness. So there is a section called incompleteness of scientific concept. Remember, I'm talking about incompleteness, not the correctness. They are correct. The concepts are correct, but they are incomplete when you go deep. For example, Heisenberg mentioned about the position and velocity, that these concepts, they work very well in Newton mechanics, but when you bring them, when you entered quantum, you saw that the limitation of these concepts. So they are good in Newton domain, but when we talk the absolute meaning of this position in terms of reality, then you find that these concepts are incomplete. This is what Heisenberg mentioned, one of our very good book, Physics and Philosophy by Heisenberg. So if you go into the basic idea is that if you see from our Indian knowledge system is that force is the concept of force which we have in modern science. We consider force just only physical. You make a 5 Newton force, push a block of mass, right? But actually in IKS, force is not only physical, there is a psychological force and there is a spiritual force. Psychological force means, for example, tomorrow is exam, but your force is you are internally pressure that I should go to a movie, very new release movie or something like that. So you have a force. So what is that force? Very subtle force inside which you experience. And then of course the spiritual force, the will or desire to do. So in our system, in our IKS says that the spiritual force about the most important all forces, will is the root cause of our being here. Willing properly in human life can lead to perfection. So this is very critical. So there is a option given in our Indian knowledge system is that proper willing can change your life direction, what you want to achieve in life. So that is why in our first scripture of Vedanta it starts with Athato Brahm Jigyasa. Now in this human life, your primary duty, other duties you have to do job, career, everything, but primary duty should be to find out the ultimate, the who is behind this cosmos. So that willing, that direction or channelizing our mind is very, very important. That's why I say force is not just physical, psychological, but spiritual. And similarly, all these concepts, if you go deep into the concept like work or velocity or motion, you will come to the same point. So in our ancient tradition, the story of universe, what is the perspective? The story of the universe which makes you a good human being. Means whatever story of universe you may have, finally it should lead you to make you a good human being. And what is the definition of good human being? Means having good qualities, which we all have some minimum inner sense of good human being: humility, compassion, gratitude, and gratitude for the universe, gratitude for other beings, even the birds and bees, because of which you cannot have pollination without them, and then without pollination you will not have vegetation, and how will you eat and survive? So those qualities, and then so this could be one of the important test, a final test of a good story, of any story of universe. If we have, irrespective of, you can include from lambda model to plasma to quarks, whatever, an ancient wisdom, but finally the irrespective of so many details you can enter, irrespective of that we can have all this together good. But final test is, as per our ancient tradition, is that whether that story is transforming you towards a good human being. That is the test of that. That is the story of universe which we get hint. There's a quote from Narlikal. I will end in 1 or 2 slides. That's all I am done. Cosmology inspires humility. There is a Narlikar that reviewing our present understanding of cosmos, an understanding that has grown considerably over the past few decades, but which cannot be considered anyway complete, of course. The subject of cosmology, which deals with the origin and evolution of the universe, tells us how small man is, how limited his experience on this tiny planet is in comparison with the physical universe that he can observe. What caused the expansion of the universe? How did galaxies come together in their clusters and superclusters? We are understanding better and better, but still, one question you solve, 20 questions new arise. We see the universe bathed in a radiation background of very low temperature. What was its origin due to? These are the questions posed by today's cosmologists. They are different from those asked by scientists of yesterday's, of even 100 years ago, when astronomy hardly reached beyond the confines of Milky Way. Have we reached the end of the quest, or does something lie beyond our galaxy? These questions and the enormity of universe in comparison with the human habitat here on the earth have had an humbling influence on some of the greatest scientific brains of this century. So this is one of the very interesting contribution of modern of cosmology, basically this field, that it really opens your mind at how small we are. Because sometimes after publishing 100 papers in top journals, or giving good theories, you forget that we are still very small, very, very small. So I end with a slide. So what our proposal is that in search for a complete story of universe, you not only need modern cosmological data, the theory, the exploration, the telescopes, you also need music, arts, as well as ancient spiritual tradition. The combined together, that you get a complete good story of the universe, where you can make a good human being, not only a good professor. You could not only make a good paper, you not only make a good human being, good professor, good position in the university, you can make a good human being, and which will be asset for sustaining this planet for the entire humanity. And there is a quote Heisenberg, that if you go deep in sciences, as Heisenberg himself went because of the quantum issues, so it is the end of his book. So there is a concluding remarks that the last slide, that experiments and experience. So experiments are necessary, but they are not sufficient to know reality. If you are really a true seeker of truth and you want to know reality within your lifetime, you cannot say, I will tell you after 1 million years, because that will not work. We have less than 100 years time. So you need to bring in experience too. The physical experiments are thought experiments. Not only physical experiments are important, but we have to bring in, but at the same time they have limitations, especially more in the field of cosmology. I cannot go to another galaxy and do the experiment. So thought experiments are equally important. They can help you not only for getting the paradox, but also the to advance our conception of reality. And then cosmology for improving mind. This is my request to all the teachers who are teaching cosmological courses, or any courses actually, but more cosmology, that besides your regular classes, not only you teach how the clusters are formed, how the Einstein's GTR, the field equations and all, in the last parts of classes, suppose you have 40 classes, in 2 classes or 3 classes of your whole course, you teach also how we should relate to universe, learning gratitude from the universe, how much our life has been sustaining by the universe, from vegetation to everything else. So that gratitude, that qualities, or our relation with the universe can also be covered in a couple of lectures when you teach cosmology. And lastly, that not only bring in anthropic principle and cosmology principle, we also need to bring in consciousness principle in our complete story of universe. So I stop and end here, and thank you for your patience to listening to us. Thank you very much.
Thank you so much, sir. It was really wonderful, very insightful and thought-provoking lecture. Bringing the thoughts and minds of these great scientists and scholars. It was really wonderful to hear that, and also you visited different issues, and how there's a need of new thought and approach. I particularly like the part where you talk about incompleteness. How it is different than not being incorrect. But incomplete. So this is widens up perspective on things. So thank you so much for this. So now I would like to invite our participants to please pose your questions. You have been already doing it during the session, but you also can scan the QR code now and quickly write your questions, which I will then forward to our speaker now. But since we already have some questions, we'd like to start with them. I will read them out to you, and then you can respond to them. The first question is from Dr. Bharat Pandey, Government PG College, Ranikhet, Uttarakhand. He says, Sir, if the universe is governed by physical laws yet gives rise to consciousness, could it be that consciousness is not just a byproduct, but a fundamental feature of the cosmos, now being extended artificially through AI in today's world? All of things
Yeah,
together.
interesting question. Thank you, Dr. Bharat. Yes, actually, consciousness is not a byproduct. You see, you take any action. For example, if I want to lift this bottle, so you have a plan. First, you make a plan in your mind, right? And so the consciousness is before it comes to the mind, the planning, and then you take a physical action. Same. Actually, very easy way to study cosmology as per our ancient tradition is that you study yourself and you will find a lot of parallels. So you see that your consciousness is the first, then it comes to the mind, and then it comes to physical action. Same like this in the universe, the consciousness is the root bottom. They must be a will, a conscious action to start the process of matter. Otherwise, like Newton's law, right? The matter remains at its rest, right? Remains at rest. So from there, then whole the process starts. So consciousness, true, it is at the roots, not at the byproduct. And as far as AI is concerned, of course, AI is nowhere near consciousness. Do not get it. We are definitely using and thankful to AI developments, and they are very useful for many fields of our human work. But AI does not have consciousness, though you Gemini or ChatGPT put thinking, but this is not thinking. Thinking is a conscious act. It is a mechanistic process, very highly advanced process. Okay.
Thank you so much for making that clear. Next question is this the same question? Oh, it's a different question, but from maybe the name is they didn't change it. Sir, in today's era of rapid technological advancement, are we solving climate change or unknowingly accelerating it? Because our mindset still treats Earth as an object to exploit rather than a relationship to sustain.
Yeah, very good question. Actually, these days my interest has moved more towards the real needs of human society. Of course, the curiosity and research is important, but I am now more interested there. Yes, definitely. So technology has both sides. Like this mobile, so the same like this mobile, it can be used for any purpose, right? You can use it for ask ChatGPT or find out some good research and do some good equation or do anything good thing, and also you can use it for wrong purposes. So any technology can be used for both purposes. That is why actually it would have been ideal that before we invent a new technology, the training of mind is given. I mean, the human mind which is going to use the technology, but unfortunately, the misuse is more than the use. So that is why the problem is. So as far as climate thing is concerned, yes, it is rooted in mind change, and so it is actually, roots are not technology, roots are our mindset. So that is why some kind of spiritual training, contemplative practices to orient our mind to use things for good. Means so technology, you will not able to stop it now. It will grow more and more as the time progresses, but you can try to channelize it in a better way, good way, as far as possible. Completely, you'll not able to eliminate the wrong side of it also, because human mind has all these tendencies too. So that is why the need of spiritual or ancient training comes in. Without that, actually, you have no way to handle human mind.
Yes. Thank you so much for that answer. So the next question is from Roshan. The question is, how is it that the same set of data can lead one scientist to infer purpose in the universe, while another concludes it is purposeless? What accounts for this difference?
Yeah, that's interesting. That also is a proof of free will you have. This is one thing, right? So the very fact that you can choose what you would like, your preference, your choices. So sometimes there's a question whether we have free will. Yes, you have free will. You can choose whether God exists or not, right? So that freedom is given. Similarly, the question which you are saying, that whether the purpose is there or not. So that is one part that you are free. Second is, data is there, but the interpretation of the data, that is very important. Actually, our founder, Dr. T.D. Singh, one time when he was doing a conference in Rome, he had a session, detailed session on theistic interpretations of data, scientific data. So like you can have scientific interpretation, you can have theistic interpretation also of the same data. So it depends on your outlook, on your worldview. So that freedom is there, we all of us have. Data is same, but how you interpret, your choices, your preferences will definitely matter. So for example, in quantum mechanics, you have parallel interpretations, right? So same phenomena, but you have so many interpretations. So that choices are there.
Yes, definitely. Thank you so much. Then the next question is from Rajesh. He is asking, is it possible to incorporate the concept of mind into mainstream science? Can mathematics or quantum physics provide a framework for doing so?
Good thing. Yeah, just today morning or earlier I was reading this book, but today morning I was just again came to my mind, came to my hand. You see this book called Our Mathematical Universe. This is Tagmar. Tagmar is MIT physicist, very prominent. So in this one of the page he mentions is a diagram called mainstream, how the boundaries of mainstream science keep on changing. This is what we call mainstream today, or what was called 100 years ago. This keeps on changing. That is one part. That mainstreams, as per the need, keeps on changing. Second part is um, this bringing in mind. Actually, we did not want, scholars, scientists did not want it to bring in, but now we are forced to bring in, because one of the areas is mental health issues. Now today you have prominent journals around the world on mental health. Today, in Nature itself, not only publishes scientific articles, they have a dedicated journal on mental health, especially in the youngsters. So already it is coming to the mainstream of science about that even though you don't understand mind in terms of the way we have been trying to reduce it to some combination of neurons, but today it seems whether we understand or not, you are not able to avoid the mind in the society, the idea of mind, which is not just a physical brain. So that is why mind is more and more, especially last 50 years, a tremendous research and work has come and is actually already entering in the mainstream of science. If you will be surprised, today neuroscience research includes more mind than the pure neurons work, because there are another area called this challenges in health. Like there are mental diseases which you cannot handle by medicine. So there again, mind comes into picture, and then There are so many now. Harvard University they collaborate with many meditational practitioners who are doing meditation to understand the workings of mind, to develop this data on mental health, on mind. So that is already a lot way further now.
Yes, thank you so much. So the next question is from Pradeep, Kendriya Vidyalaya Sangathan. He asks, Varunji, thank you so much for such a profound lecture. If consciousness, matter, and energy are distinct, by what mechanism do they interact? Conversely, if they are expression of a single essence, what special informational or geometric rules dictate how the absolute precipitates into the structured material world?
You please keep the question on the screen. Lot of points are
Yes.
there in this.
Yes.
Yeah, a lot of interesting points are there. One is very clear as per our Vedic tradition. Matter and spirit are two distinct categories, fundamental categories of universe. Like your time and space, right? Not time and space. I can say, give another example. Okay, leave it. The matter and spirit or consciousness are two distinct fundamental categories which exist all the time. So matter manifests for some time, that doesn't manifest but remain in unmanifested form, and consciousness remains all the time. That is number one. Number two, energy and matter, you already know they are interchangeable, E equal to mc square. So that's not a problem. Number three, the consciousness interacting with the matter universe, it is a very big mystery. We don't know actually how it happens. For example, so you can refer to a lot of details are there, but we don't know how it happens. One of the things which we are finding useful, which you may find useful, one of our research scholars is also working in that area, is that quantum information area. So that information, how it passes from consciousness to, because the things become very subtle and subtle, from matter to the mind to the intelligence to deeper into consciousness. So this could be helpful, that quantum information area, about how the information passes from consciousness to the matter. So that is what we don't know. That is for sure. And as far as Vedic things are concerned, you can go roots of, you can read, I think yesterday was my colleague showed Vasudev Rao that about Bhagavatam, some of the references. So some of those things are given, that how they unfold from consciousness to the mind to the physical, then these all these Panchabhutas, the physical structures, but not the kind of details which you will look for. For example, it will not give you the Schrodinger equation or uncertainty equation, but it will give you basic idea. Also, these are the things I can say about this question. But very good question, and it has a lot of deep insight.
Yes, thank you. Thank you for the question, and thank you also for the answer. So, I mean, we have many questions, but again, due to time, I will just ask one last question. Um, let's see if we can put up the question. Okay. So the question is from Devjit, DMC College, Kolkata. It's a short one. Could the universe itself possess a form of consciousness?
Universal. So the question depends on what do you mean by universe? So our general conception universe has been the physical structure which I would see there, that which I can touch, the earth I can touch, right? But universe is not just this, which you can touch. Universe also, like your body, you not only include this physical body which you can touch, there is also mind you have, which you make planning, thinking, right? Similarly, universe also is not just a physical structure which you can touch, which we study. There's also a mental aspect of that. So if you go in that aspect, then definitely then you go to further aspect, that universe actually is rooted in consciousness. So when I say universe physical, universe psychological, universe spiritual means at the root of universe is actually consciousness. But consciousness is different from universe also. That is very important. Means consciousness, as per our Vedic tradition, is purely distinct category than the physical matter or the subtle matter mind. So that much I can say.
Thank you so much once again for this very amazing lecture. It was very clear. Everyone, I'm sure, understood it very nicely. And thank you so much for taking time out and presenting this to us. So with this, let me share my screen. So we are towards the end of our today's particular session. An amazing day with three amazing lectures in string theory, cosmology, and again consciousness. So a quick review, a preview for tomorrow. We will continue our extraordinary journey with this profound and rich lineup for day 7, our final and concluding day. So please join us to explore this final day. I'm also, I should really mention this, that I'm so happy that the number of participants remained constant throughout the last 3 hours. It only went higher. So this was really good. So thank you all for staying with us. And tomorrow we will have again an amazing lineup of talks, starting with cosmology in Vedic tradition from Professor Manoranjan Sinha, who's from IIT Kharagpur. Then we have concept of physical time in the Vedas from Professor R.N. Iyengar, Center of Ancient History and Culture, Jain University, Bangalore. Then we'll have essential features of Indian astronomy from Professor M. S. Sriram, um, President Professor K.V. Sarma Research Foundation, Chennai. And then the last talk tomorrow, titled A Voyage Through Our Heliosphere to Study Our Nearest Star, the Sun. Professor Dipankar Banerjee, Vice Chancellor, IIST, Trivandrum. So this is an amazing lineup tomorrow. Please join us for that. We hope to see you more. And then before again I conclude, I would like to give you a quick description of some of the publications from Bhaktivedanta Institute. So here, this is a publication magazine of Bhaktivedanta Institute, Tattva Jigyasa, Science and Spiritual Quest for Ultimate Reality. It's a volume 4, and it has these two amazing segments. First, there's a dialogue and expedition into the secrets of the universe, featuring the legendary Professor Freeman Dyson. This discourse invites us to peer through the eyes of one of the history's greatest visionaries as he unravels the fundamental mysteries governing our existence, covering various aspects ranging from origin of life to astronomy, discovery of numerous planets in the universe, and many more. Complementing this journey is the beautiful article which is called The IQ of Our Universe by Dr. Gerald L. Schroeder, an esteemed MIT physicist. Dr. Schroeder challenges our perception of cosmos, asking us to consider whether the universe itself possesses an inherent structure intelligence, which is also somehow related to the last question of the last talk today. Together, these works serve as a bridge between rigorous scientific inquiry and the eternal quest for meaning, reminding us that the more we discover, the more we stand in awe of the sublime design of our reality. So please visit the store.beans.org to know more about this publication. One more thing that we would like to mention is the video course on exploring the secrets of our universe. This technical video course offers a comprehensive, around 200 minutes breakdown of modern cosmology across 5 intensive sessions. It focuses on physics of time, the fine-tuning of physical constant, and the multidimensional nature of cosmic reality. So the course is led by an elite faculty of global researchers, Professor Craig Callender, University of California. We have Professor Ram Gopal Paluri, IIT Guwahati. We have Professor Viknesh Krishnan Kuti from Celivate Technology, Singapore. We have Professor Manoranjan Sinha, IIT Kharagpur, Professor Hare Krishna Mohanta Vits Pilani, all expert in different fields like philosophy of time, logic of time, chemical and physical systems, biological and physical structures, process control and system engineering. So please, again, you can visit www.beans.org/exploring universe. Once again, to remind you, tomorrow the final session, final day of this voyage starts at 10 a.m. as today. And please join us to witness this wonderful session tomorrow. And once again, we extend our gratitude to all our speakers, the dignitaries, guests, and all our participants for joining us today. And looking forward to see you all in tomorrow's session. Thank you all for joining.